Don Smith. While much of what Don Smith said is undoubtedly true, I am not convinced that his claims of what he actually achieved personally are true. Please bear that in mind. Don died in 2004. Don Smith is elderly and has suffered several serious strokes in the last few years. He is no longer able to respond to emails, and his website has been taken over by people who appear very keen to ensure that his work and information can no longer be accessed by members of the public. At this point in time, there is very little information available on Don's achievements. What I have been able to locate is 4 video recordings of lectures which he gave, plus a copy of his PDF document entitled Resonance Energy Systems. There is also a website with limited information. This site appears to have been set up by Don's son, whom I suspect does not fully understand how his father's devices work. Don has produced at least 48 different devices which draw energy from what Don prefers to call the ambient background. His devices are capable of supplying kilowatts of excess energy, and in most cases they do not require any input energy to be supplied by the user. It is said that 40,000 copies of Don's PDF document have been sold worldwide, but it appears that it is no longer possible to buy a copy, and for that reason, a copy is contained within this document. Please be aware that Don states quite openly that he does not disclose all of the details on any of his devices in his public discussions. This is because the rights to each device have been assigned to a different company in which Don has a financial interest, and so it is not in his interests to disclose the full details. However, Ha says that he discloses enough for somebody who is experienced in radio frequency electronics to be able to deduce the things which he does not disclose, and so build a device for his own use. If that is the case, then anybody who has succeeded in doing so has kept very quiet about it afterwards, which is understandable. Having said that, Tyrell Kopanads of Georgia appears to have replicated one of the designs, although it is quite likely that Tyrell deduced the operating principles for himself. These principles are clearly based on the work of Nikola Tesla. In Don's work, he refers to the educational kit entitled Resonance Circuits No. 10, 416 from the science source at www.thescience.com. That kit now costs $100, and they don't mention the fact that you need a signal generator capable of producing a 10-volt output at up to 1 MHz in order to be able to do resonance tests, and the kit now uses an LED rather than a neon bulb. Don says that his understanding comes from the work of Nikola Tesla as recorded in Thomas E. Martin's book The Inventions, Researches, and Writings of Nikola Tesla, ISBN 0-7873-0582-0, available from http://www.healthresearchbooks.com and various other book companies. This book can be downloaded from http://www.free-energy-info.com as a PDF file, but a paper copy is much better quality and easier to work from. Don states that he repeated each of the experiments found in the book, and that gave him his understanding of what he prefers to describe as the ambient background energy, which is called the zero-point energy field elsewhere in this e-book. Don remarks that he has now advanced further than Tesla in this field, partly because of the devices now available to him and which were not available when Tesla was alive. Don stresses 2 key points. Firstly, a dipole can cause a disturbance in the magnetic component of the ambient background, and that imbalance allows you to collect large amounts of electrical power, using capacitors and inductors, coils. Secondly, you can pick up as many powerful electrical outputs as you want from that one magnetic disturbance, without depleting the magnetic disturbance in any way. This allows massively more power output than the small power needed to create the magnetic disturbance in the first place. This is what produces a COP greater than 1 device, and Don has created nearly 50 different devices based on that understanding. Although they get removed quite frequently, there is one video which is definitely worth watching if it is still there. It is located at http://www.metacafé.com/watch/2820531/don_smith_free_energy and was recorded in 2006. It covers a good deal of what Don has done. In the video, reference is made to Don's website, but you will find that it has been taken over by Big Oil, who have filled it with innocuous similar sounding things of no consequence, apparently intended to confuse newcomers. A website which is run by Connie Ostrom of Sweden is http://www.johnnyfg.110mb.com, and it has brief details of his prototypes and theory. You will find the only document of his which I could locate here, http://www.free-energy-info.com/smith.pdf in PDF format, and it contains the following patent on a most interesting device which appears to have no particular limit on the output power. This is a slightly reworded copy of that patent, as patents are generally worded in such a way as to make them difficult to understand. Patent NL02000035A, May 20, 2004. Inventor, Donald Lee Smith. Transformer generator magnetic resonance into electric energy. Abstract. The present invention refers to an electromagnetic dipole device and method, where wasted radiated energy is transformed into useful energy. A dipole, as seen in antenna systems, is adapted for use with capacitor plates in such a way that the heaviside current component becomes a useful source of electrical energy. Description. Technical field. This invention relates to loaded dipole antenna systems and their electromagnetic radiation. When used as a transformer with an appropriate energy collector system, it becomes a transformer/generator. The invention collects and converts energy which is radiated and wasted by conventional devices. Background art. A search of the International Patent Database for closely related methods did not reveal any prior art with an interest in conserving radiated and wasted magnetic waves as useful energy. Disclosure of the invention. The invention is a new and useful departure from transformer generator construction, such that radiated and wasted magnetic energy changes into useful electrical energy. Gauss meters show that much energy from conventional electromagnetic devices is radiated into the ambient background and wasted. In the case of conventional transformer generators, a radical change in the physical construction allows better access to the energy available. It is found that creating a dipole and inserting capacitor plates at right angles to the current flow allows magnetic waves to change back into useful electrical, coulombs, energy. Magnetic waves passing through the capacitor plates do not degrade, and the full impact of the available energy is accessed. 1, or as many sets of capacitor plates as is desired, may be used. Each set makes an exact copy of the full force and effect of the energy present in the magnetic waves. The originating source is not depleted of degraded as is common in conventional transformers. Brief description of the drawings. The dipole at right angles allows the magnetic flux surrounding it to intercept the capacitor plate, or plates, at right angles. The electrons present are spun such that the electrical component of each electron is collected by the capacitor plates. Essential parts are the south and north component of an active dipole. Examples presented here exist as fully functional prototypes and were engineer constructed and fully tested in use by the inventor. In each of the three examples shown in the drawings, corresponding parts are used. Fig 1 is a view of the method, where N is the north and S is the south component of the dipole. Here, 1 marks the dipole with its north and south components. 2 is a resonant high-voltage induction coil. 3 indicates the position of the electromagnetic wave emission from the dipole. 4 indicates the position and flow direction of the corresponding heaviside current component of the energy flow caused by the induction coil. 2. 5 is the dielectric separator for the capacitor plate. 7. 6 for the purposes of this drawing, indicates a virtual limit for the scope of the electromagnetic wave energy. In Fig 2a1 is the hole in the capacitor plates through which the dipole is inserted, and in Fig 2b it is the dipole with its north and south poles shown. 2 is the resonant high-voltage induction coil surrounding part of the dipole. 1. The dielectric separator. 5 is a thin sheet of plastic placed between the two capacitor plates. 7 the upper plate being made of aluminium and the lower plate made of copper. Unit 8 is a deep cycle battery system powering a DC inverter 9 which produces 120 volts at 60 Hz, the US main supply voltage and frequency. Obviously, a 240 volt 50 Hz inverter could be used here just as easily, which is used to power whatever equipment is to be driven by the device. The reference number 10 just indicates connecting wires. Unit 11 is a high voltage generating device such as a neon transformer with its oscillating power supply. Fig 3 is a proof of principle device using a plasma tube as an active dipole. In this drawing, 5 is the plastic sheet dielectric separator of the two plates 7 of the capacitor, the upper plate being aluminium and the lower plate copper. The connecting wires are marked 10 and the plasma tube is designated 15. The plasma tube is 4 feet long, 1.22 m, and 6 inches, 150 mm, in diameter. The high voltage energy source for the active plasma dipole is marked 16 and there is a connector box 17 shown as that is a convenient method of connecting to the capacitor plates when running tests on the device. Fig 4 shows a manufacturer's prototype, constructed and fully tested. 1 is a metal dipole rod and 2 the resonant high voltage induction coil, connected through wires 10 to connector block 17 which facilitates the connection of its high voltage power supply. Clamps 18 hold the upper edge of the capacitor packet in place and 19 is the base plate with its supporting brackets which hold the whole device in place. 20 is a housing which contains the capacitor plates and 21 is the point at which the power output from the capacitor plates is drawn off and fed to the DC inverter. Best method of carrying out the invention. The invention is applicable to any and all electrical energy requirements. The small size and its high efficiency make it an attractive option, especially for remote areas, homes, office buildings, factories, shopping centers, public places, transportation, water systems, electric trains, boats, ships and all things great and small. The construction materials are commonly available and only moderate skill levels are needed to make the device. Claims. 1. Radiated magnetic flux from the dipole, when intercepted by capacitor plates at right angles, changes into useful electrical energy. 2. A device and method for converting for use, normally wasted electromagnetic energy. 3. The dipole of the invention is any resonating substance such as metal rods, coils and plasma tubes which have interacting positive and negative components. 4. The resulting heaviside current component is changed to useful electrical energy. This patent does not make it clear that the device needs to be tuned and that the tuning is related to its physical location. The tuning will be accomplished by applying a variable frequency input signal to the neon transformer and adjusting that input frequency to give the maximum output. Don Smith has produced some 48 different devices, and because he understands that the real power in the universe is magnetic and not electric, these devices have performances which appear staggering to people trained to think that electrical power is the only source of power. The device shown below is physically quite small and yet it has an output of 160 kilowatts, 8000 volts at 20 amps, from an input of 12 volts 1 amp, COP equal 13,333. This is a device which can be placed on top of a table and is not a complicated form of construction, having a very open and simplistic layout. However, some components are not mounted on this board. The 12-volt battery and connecting leads are not shown, nor are the ground connections, the step-down isolation transformer and the varistor used to protect the load from overvoltage by absorbing any random induced voltage spikes which might occur. The device shown above has various subtle points glossed over in spite of this being one device which Don says that we should be able to reproduce ourselves. Let me state here that reproducing this seemingly simple design of Don's is not an easy thing to do and it is not something which can be thrown together by a beginner using whatever components happen to be at hand at the time. Having said that, with careful study and common sense application of some obvious facts, it should be possible to make one of these devices, but more of these things later on when a much more detailed description of this device is given. Another of Don's devices, somewhat similar to the one described in his patent, is shown here. This is a larger device which uses a plasma tube 4 feet, 1.22 meters, long and 6 inches, 150 millimeter, in diameter. The output is a massive 100 kilowatts. This is the design shown as one of the options in Don's patent. Being an electrical engineer, none of Don's prototypes are in the toy category. If nothing else is taken from Don's work, we should realize that high power outputs can be had from very simple devices. There is one other brief document, Resonate Electrical Power System from Don Smith, which says, potential energy is everywhere at all times, becoming useful when converted into a more practical form. There is no energy shortage, only gray matter. This energy potential is observed indirectly through the manifestation of electromagnetic phenomenon, when intercepted and converted, becomes useful. In nonlinear systems, interaction of magnetic waves amplify, conjugate, energy, providing greater output than input. In simple form, in the piano where 3 strings are struck by the hammer, the center one is impacted and resonance activates the side strings. Resonance between the 3 strings provides a sound level greater than the input energy. Sound is part of the electromagnetic spectrum and is subject to all that is applicable to it. Useful energy is defined as that which is other than ambient. Electric potential relates to mass and its acceleration. Therefore, the Earth's mass and speed through space gives it an enormous electrical potential. Humans are like the bird sitting unaware on a high voltage line. In nature, turbulence upsets ambient and we see electrical displays. Tampering with ambient allows humans to convert magnetic waves into useful electricity. Putting this in focus requires a look at the Earth in general. During each of the 1,440 minutes of each day, more than 4,000 displays of lightning occur. Each display yields more than 10 million volts at more than 200,000 amperes in equivalent electromagnetic flux. This is more than 57,600,000,000,000 volts and 1,152,000,000,000 amperes of electromagnetic flux during each 24-hour period. This has been going on for more than 4 billion years. The USPTO insists that the Earth's electrical field is insignificant and useless, and that converting this energy violates the laws of nature. At the same time, they issue patents in which electromagnetic flux coming in from the sun is converted by solar cells into DC energy. Aeromagnetic flux, in gammas, maps worldwide, includes those provided by the U.S. Department of Interior Geological Survey, and these show clearly that there is present a spread of 1,900 gamma above ambient, from reading instruments flown 1,000 feet above the surface source. Coulomb's law requires the squaring of the distance of the remote reading, multiplied by the recorded reading. Therefore, that reading of 1,900 gamma has a corrected value of 1,900 x 1,000 x 1,000 equal 1,900,000,000 gamma. There is a tendency to confuse gamma ray with gamma. Gamma is ordinary, everyday magnetic flux, while gamma ray is high impact energy and not flux. 1 gamma of magnetic flux is equal to that of 100 volts RMS. To see this, take a plasma globe emitting 40,000 volts. When properly used, a gamma meter placed nearby will read 400 gammas. The 1,900,000,000 gamma just mentioned is the magnetic ambient equivalent of 190 million volts of electricity. This is on a solar quiet day. On solar active days it may exceed 5 times that amount. The establishment's idea that the Earth's electrical field is insignificant goes the way of their other great ideas. There are 2 kinds of electricity, potential and useful. All electricity is potential until it is converted. The resonant fluxing of electrons activates the electrical potential which is present everywhere. The intensity/CPS of the resonant frequency flux rate sets the available energy. This must then be converted into the required physical dimensions of the equipment being used. For example, energy arriving from the sun is magnetic flux, which solar cells convert to DC electricity, which is then converted further to suit the equipment being powered by it. Only the magnetic flux moves from point A, the sun, to point B, the earth. All electrical power systems work in exactly the same way. Movement of coils and magnets at point A, the generator, fluxes electrons, which in turn, excite electrons at point B, your house. None of the electrons at point A are ever transmitted to point B. In both cases, the electrons remain forever intact and available for further fluxing. This is not allowed by Newtonian physics, electrodynamics and the laws of conservation. Clearly, these laws are all screwed up and inadequate. In modern physics, USPTO style, all of the above cannot exist because it opens a door to over-unity. The good news is that the PTO has already issued hundreds of patents related to light amplification, all of which are over unity. The dynode used to adjust the self-powered shutter in your camera, receives magnetic flux from light which dislodges electrons from the cathode, reflecting electrons through the dynode bridge to the anode, resulting in billions of more electrons out than in. There are currently 297 direct patents issued for this system, and thousands of peripheral patents, all of which support over unity. More than 1,000 other patents which have been issued, can be seen by the discerning eye to be over unity devices. What does this indicate about intellectual honesty? Any coil system, when fluxed, causes electrons to spin and produce useful energy, once it is converted to the style required by its use. Now that we have described the method which is required, let us now see how this concerns us. The entire system already exists and all that we need to do is to hook it up in a way which is useful to our required manner of use. Let us examine this backwards and start with a conventional output transformer. Consider one which has the required voltage and current handling characteristics and which acts as an isolation transformer. Only the magnetic flux passes from the input winding to the output winding. No electrons pass through from the input side to the output side. Therefore, we only need to flux the output side of the transformer to have an electrical output. Bad design by the establishment, allowing hysteresis of the metal plates, limits the load which can be driven. Up to this point, only potential is a consideration. Heat, which is energy loss, limits the output amperage. Correctly designed composite cores run cool, not hot. A power correction factor system, being a capacitor bank, maintains an even flow of flux. These same capacitors, when used with a coil system, a transformer, become a frequency timing system. Therefore, the inductance of the input side of the transformer, when combined with the capacitor bank, provides the required fluxing to produce the required electrical energy, cycles per second. With the downstream system in place, all that is needed now is a potential system. Any flux system will be suitable. Any amplification over unity output type is desirable. The input system is point A and the output system is point B. Any input system where a lesser amount of electrons disturbs a greater amount of electrons, producing an output which is greater than the input, is desirable. At this point, it is necessary to present updated information about electrons and the laws of physics. A large part of this originates from me, Don Smith, and so is likely to upset people who are rigidly set in the thought patterns of conventional science. Non-ionic electrons. As a source of electrical energy, non-ionic electrons doublets exist in immense quantities throughout the universe. Their origin is from the emanation of solar plasma. When ambient electrons are disturbed by being spun or pushed apart, they yield both magnetic and electrical energy. The rate of disturbance, cycling, determines the energy level achieved. Practical methods of disturbing them include moving coils past magnets or vice versa. A better way is the pulsing, resonant induction, with magnetic fields and waves near coils. In coil systems, magnetic and amperage are one package. This suggests that electrons in their natural non-ionic state exist as doublets. When pushed apart by agitation, one spins right, yielding volts potential electricity, and the other spins left, yielding amperage magnetic energy, one being more negative than the other. This further suggests that when they reunite, we have volts times amps equal watts, useful electrical energy. Until now, this idea has been totally absent from the knowledge base. The previous definition of amperage is therefore flawed. Electron-related energy. Left-hand spin of electrons results in electrical energy and right-hand spin results in magnetic energy. Impacted electrons emit visible light and heat. Useful circuits, suggestions for building an operational unit. 1. Substitute a plasma globe such as Radio Shack's Illuministorm for the source resonant induction system. It will have about 400 milligauss of magnetic induction. 1 milligauss is equal to 100 volts worth of magnetic induction. 2. Construct a coil using a 5-inch to 7-inch, 125 to 180 mm, diameter piece of PVC for the coil former. 3. Get about 30 feet, 10 m, of jumbo speaker cable and separate the two strands. This can be done by sticking a carpet knife into a piece of cardboard or wood, and then pulling the cable carefully past the blade to separate the two insulated cores from each other. PJK note: jumbo speaker cable is a vague term as that cable comes in many varieties, with anything from a few, to over 500 strands in each core. 4. Wind the coil with 10 to 15 turns of wire and leave about 3 feet, 1 m, of cable spare at each end of the coil. Use a glue gun to hold the start and finish of the coil. 5. This will become the L2 coil shown in the circuits page. 6. When sitting on top of the plasma globe, like a crown, you have a first-class resonant air core coil system. 7. Now, substitute 2 or more capacitors, rated at 5000 volts or more, for the capacitor bank shown on the circuits page. I use more than 234 microfarad capacitors. 8. Finish out the circuit as shown. You are now in business. 9. Voltage, amperage limiting resistors are required across the output side of the load transformer. These are used to adjust the output level and the desired cycles per second. Don Smith's suggestions: get a copy of the Handbook of Electronic Tables and Formulas, published by SAMS, ISBN 0-672-22469-0, also an inductance/capacitance/resistance meter is required. Chapter 1 of Don's PDF document has important time constant, frequency, information and a set of reactance charts in nomograph style. Nomograph, a graph, usually containing 3 parallel scales graduated for different variables so that when a straight line connects values of any two, the related value may be read directly from the third at the point intersected by the line, which makes working and approximating of the 3 variables, capacitance, inductance, and resistance, much easier. If 2 of the variables are known, then the third one can be read from the nomograph. For example, if the input side of the isolation transformer needs to operate at 60 Hz, that is 60 positive cycles and 60 negative cycles, being a total of 120 cycles. Read off the inductance in henries by using an inductance meter attached to the input side of the isolation transformer. Plot this value on the nomographic reactance chart. Plot the needed 120 Hz on the chart and connect these 2 points with a straight line. Where this line crosses the farads line and the ohms line, gives us 2 values. Choose one resistor, and insert it between the 2 leads of the transformer input winding. The power correction factor capacitor, or bank of more than one capacitor, now needs adjusting. The following formula is helpful in finding this missing information. The capacitance is known, as is the desired potential to pulse the output transformer. 1 farad of capacitance is 1 volt for 1 second, 1 coulomb. Therefore, If we want to keep the bucket full with a certain amount, how many dippers full are needed? If the bucket needs 120 volts, then how many coulombs are required? Now, go to the nomograph mentioned above, and find the required resistor jumper to place between the poles of the correction factor capacitor. An earth grounding is desirable, acting as both a voltage limiter and a transient spike control. Two separate earths are necessary, one at the power factor capacitor and one at the input side of the isolation transformer. Off-the-shelf surge arresters/spark gaps and varistors having the desired voltage/potential and amperage control are commonly available. Siemens, Seidel America and others, make a full range of surge arresters, etc. Varistors look like coin-sized flat capacitors. Any of these voltage limiters are marked as V1 in the following text. It should be obvious that several separate closed circuits are present in the suggested configuration: the power input source, the high voltage module, a power factor capacitor bank combined with the input side of the isolation transformer. Lastly, the output side of the isolation transformer and its load. None of the electrons active at the power source, battery, are passed through the system for use downstream. At any point, if the magnetic flux rate should happen to vary, then the number of active electrons also varies. Therefore, controlling the flux rate controls the electron potential activity. Electrons active at point A are not the same electrons which are active at point B, or those at point C, and so on. If the magnetic flux rate, frequency Hertz, varies, then a different number of electrons will be disturbed. This does not violate any natural law and it does produce more output energy than the input energy, should that be desirable. A convenient high-voltage module is a 12-volt DC neon tube transformer. The power factor correction capacitors should be as many microfarads as possible, as this allows a lower operating frequency. The 12-volt neon tube transformer oscillates at about 30,000 Hz. At the power correction factor capacitor bank we lower the frequency to match the input side of the isolation transformer. Other convenient high-voltage sources are car ignition coils, television flyback transformers, laser printer modules, and various other devices. Always lower the frequency at the power factor correction capacitor and correct, if needed, at the input side of the isolation transformer. The isolation transformer comes alive when pulsed. Amperage becomes a part of the consideration only at the isolation transformer. Faulty design, resulting in hysteresis, creates heat which self-destructs the transformer if it is overloaded. Transformers which have a composite core instead of the more common cores made from many layers of thin sheets of soft iron, run cool and can tolerate much higher amperage. The information shown above relates to the small suitcase model demonstrated at the 1996 Tesla convention, presented as Don Smith's workshop. This unit was a very primitive version and newer versions have atomic batteries and power output ranges of gigawatts. The battery requirement is low level and is no more harmful than the radium on the dial of a clock. Commercial units of Boulder Dam size are currently being installed at several major locations throughout the world. For reasons of Don's personal security and contract obligations, the information which he has shared here is incomplete. PJK, I am most definitely not an expert in this area. However, it is probably worth mentioning some of the main points which Don Smith appears to be making. There are some very important points being made here, and grasping these may make a considerable difference to our ability to tap into the excess energy available in our local environment. There are 4 points worth mentioning. 1. Voltage. 2. Frequency. 3. Magnetic-electric relationship. 4. Resonance. 1. Voltage. We tend to view things with an intuitive view, generally based on fairly simple concepts. For example, we automatically think that it is more difficult to pick up a heavy object than to pick up a light one. How much more difficult? Well, if it is twice as heavy, it would probably be about twice as much effort to pick it up. This view has developed from our experience of things which we have done in the past, rather than on any mathematical calculation or formula. Well, how about pulsing an electronic system with a voltage? How would the output power of a system be affected by increasing the voltage? Our initial off-the-cuff reaction might be that the power output might be increased a bit, but then hold on, we've just remembered that watts equal volts x amps, so if you double the voltage, then you would double the power in watts. So we might settle for the notion that if we doubled the voltage then we could double the output power. If we thought that, then we would be wrong. Don Smith points out that as capacitors and coils store energy, if they are involved in the circuit, then the output power is proportional to the square of the voltage used. Double the voltage, and the output power is 4 times greater. Use 3 times the voltage and the output power is 9 times greater. Use 10 times the voltage and the output power is 100 times greater. Don says that the energy stored, multiplied by the cycles per second, is the energy being pumped by the system. Capacitors and inductors, coils, temporarily store electrons, and their performance is given by capacitor formula, W equals 0.5 x Cx V2 x Hz, where W is the energy in joules, joules equal volts x amps x seconds. C is the capacitance in farads. V is the voltage. Hertz is the cycles per second. Inductor formula, W equals 0.5 x L x A2 x Hz, where W is the energy in joules. L is the inductance in henries. A is the current in amps. Hertz is the frequency in cycles per second. You will notice that where inductors, coils, are involved, then the output power goes up with the square of the current. Double the voltage and double the current gives 4 times the power output due to the increased voltage, and that increased output is increased by a further 4 times due to the increased current, giving 16 times the output power. 2. Frequency. You will notice from the formulas above, that the output power is directly proportional to the frequency Hertz. The frequency is the number of cycles per second, or pulses per second, applied to the circuit. This is something which is not intuitive for most people. If you double the rate of pulsing, then you double the power output. When this sinks in, you suddenly see why Nikola Tesla tended to use millions of volts and millions of pulses per second. However, Don Smith states that when a circuit is at its point of resonance, resistance in the circuit drops to zero and the circuit becomes effectively a superconductor. The energy for such a system which is in resonance is resonance circuit, W equals 0.5 x Cx V2 x Hz, 2, where W is the energy in joules. C is the capacitance in farads. V is the voltage. Hertz is the cycles per second. If this is correct, then raising the frequency in a resonating circuit has a massive effect on the power output of the device. The question then arises, why is the mains power in Europe just 50 cycles per second and in America just 60 cycles per second? If power goes up with frequency, then why not feed households at 1,000,000 cycles per second? One major reason is that it is not easy to make electric motors which can be driven with power delivered at that frequency, so a more suitable frequency is chosen in order to suit the motors in vacuum cleaners, washing machines and other household equipment. However, if we want to extract energy from the environment, then we should go for high voltage and high frequency. Then, when high power has been extracted, if we want a low frequency suited to electric motors, we can pulse the already captured power at that low frequency. It might be speculated that if a device is being driven with sharp pulses which have a very sharply rising leading edge, that the effective frequency of the pulsing is actually determined by the speed of that rising edge, rather than the rate at which the pulses are actually generated. For example, if pulses are being generated at, say, 50 kHz but the pulses have a leading edge which would be suited to a 200 kHz pulse train, then the device might well see the signal as a 200 kHz signal with a 25% mark/space ratio, the very suddenness of the applied voltage having a magnetic shocking effect equivalent to a 200 kHz pulse train. 3. Magnetic/electric relationship. Don states that the reason why our present power systems are so inefficient is because we concentrate on the electric component of electromagnetism. These systems are always COP less than 1, as electricity is the losses of electromagnetic power. Instead, if you concentrate on the magnetic component, then there is no limit on the electric power which can be extracted from that magnetic component. Contrary to what you might expect, if you install a pickup system which extracts electrical energy from the magnetic component, you can install any number of other identical PIC UPS, each of which extract the same amount of electrical energy from the magnetic input, without loading the magnetic wave in any way. Unlimited electrical output for the cost of creating a single magnetic effect. The magnetic effect which we want to create is a ripple in the zero-point energy field, and ideally, we want to create that effect while using very little power. Creating a dipole with a battery which has a plus and a minus terminal, or a magnet which has north and south poles, is an easy way to create an electromagnetic imbalance in the local environment. Pulsing a coil is probably an even better way, as the magnetic field reverses rapidly if it is an air core coil, such as a Tesla coil. Using a ferromagnetic core to the coil can create a problem, as iron can't reverse its magnetic alignment very rapidly, and ideally, you want pulsing which is at least 1,000 times faster than iron can handle. Don draws attention to the transmitter-receiver educational kit Resonance Circuits number 10, 416, which was supplied by the Science Source, Maine. This kit demonstrated the generation of resonant energy and its collection with a receiver circuit. However, if several receiver circuits are used, then the energy collected is increased several times without any increase in the transmitted energy. This is similar to a radio transmitter where hundreds of thousands of radio receivers can receive the transmitted signal without loading the transmitter in any way. In Don's day, this kit was driven by a 1.5 volt battery and lit a 60 watt bulb which was supplied. Not surprisingly, that kit has been discontinued and a trivial kit substituted. If you get the Science Source educational kit, then there are some details which you need to watch out for. The unit has two very nice quality plastic bases and two very neatly wound coils, each of 60 turns of 0.47 mm diameter enameled copper wire on clear acrylic tubes 57 mm, 225, in diameter. The winding covers a 28 mm section of the tube. The layout of the transmitter and receiver modules does not match the accompanying instruction sheet, and so considerable care needs to be taken when wiring up any of their circuits. The circuit diagrams are not shown, just a wiring diagram, which is not great from an educational point of view. The one relevant circuit is: before you buy the kit, it is not mentioned that in order to use it, you now need a signal generator capable of producing a 10-volt signal at 1 MHz. The coil has a DC resistance of just 1.9 ohms, but at a 1 MHz resonant frequency, the necessary drive power is quite low. A variable capacitor is mounted on the receiver coil tube, but the one in my kit made absolutely no difference to the frequency tuning, nor was my capacitance meter able to determine any capacitance value for it at all, even though it had no trouble at all in measuring the 101 picofarad capacitor, which was exactly the capacitance printed on it. For that reason, it is shown in blue in the circuit diagram above. Disconnecting it made no difference whatsoever. In this particular kit, standard screw connectors have had one screw replaced with an Allen key-headed bolt which has a head large enough to allow finger tightening. Unfortunately, those bolts have a square cut tip where a dome tip is essential if small diameter wires are to be clamped securely. If you get the kit, then I suggest that you replace the connectors with a standard electrical screw connector strip. In tests, the LED lights up when the coils are aligned and within about 100 mm of each other, or if they are closed together side by side. This immediately makes the Hubbard device spring to mind. Hubbard has a central electromagnetic transmitter surrounded by a ring of receivers closely coupled magnetically to the transmitter, each of which will receive a copy of the energy sent by the transmitter. Don points to an even more clearly demonstrated occurrence of this effect in the Tesla coil. In a typical Tesla coil, the primary coil is much larger diameter than the inner secondary coil. If, for example, 8000 volts is applied to the primary coil which has 4 turns, then each turn would have 2000 volts of potential. Each turn of the primary coil transfers electromagnetic flux to every single turn of the secondary winding, and the secondary coil has a very large number of turns. Massively more power is produced in the secondary coil than was used to energize the primary coil. A common mistake is to believe that a Tesla coil can't produce serious amperage. If the primary coil is positioned in the middle of the secondary coil as shown, then the amperage generated will be as large as the voltage generated. A low power input to the primary coil can produce kilowatts of usable electrical power as described in Chapter 5. 4. Resonance. An important factor in circuits aimed at tapping external energy is resonance. It can be hard to see where this comes in when it is an electronic circuit which is being considered. However, everything has its own resonant frequency, whether it is a coil or any other electronic component. When components are connected together to form a circuit, the circuit has an overall resonant frequency. As a simple example, consider a swing. If the swing is pushed before it reaches the highest point on the mother's side, then the push actually opposes the swinging action. The time of one full swing is the resonant frequency of the swing, and that is determined by the length of the supporting ropes holding the seat and not the weight of the child nor the power with which the child is pushed. Provided that the timing is exactly right, a very small push can get a swing moving in a substantial arc. The key factor is matching the pulses applied to the swing, that is, to the resonant frequency of the swing. Get it right and a large movement is produced. Get it wrong, and the swing doesn't get going at all, at which point, critics would say see swings just don't work, this proves it. Establishing the exact pulsing rate needed for a resonant circuit is not particularly easy, because the circuit contains coils, which have inductance, capacitance and resistance, capacitors, which have capacitance and a small amount of resistance, and resistors and wires, both of which have resistance and some capacitance. These kinds of circuit are called LRC circuits because L is the symbol used for inductance, R is the symbol used for resistance and C is the symbol used for capacitance. Don Smith provides instructions for winding and using the type of air core coils needed for a Tesla coil. He says: 1. Decide a frequency and bear in mind the economy of the size of construction selected. The factors are: A. Use radio frequency, above 20 kHz. B. Use natural frequency, i.e. match the coil wire length to the frequency, coils have both capacitance and inductance. C. Make the wire length either 1/4, 1/2 of the full wavelength. D. Calculate the wire length in feet as follows. If using 1/4 wavelength, then divide 247 by the frequency in megahertz. If using 1/2 wavelength, then divide 494 by the frequency in megahertz. If using the full wavelength, then divide 998 by the frequency in megahertz. For wire lengths in meters. If using 1/4 wavelength, then divide 75.29 by the frequency in megahertz. If using 1/2 wavelength, then divide 150.57 by the frequency in megahertz. If using the full wavelength, then divide 304.19 by the frequency in megahertz. 2. Choose the number of turns to be used in the coil when winding it using the wire length just calculated. The number of turns will be governed by the diameter of the tube on which the coil is to be wound. Remember that the ratio of the number of turns in the L1 and L2 coils controls the overall output voltage. For example, if the voltage applied the large outer coil L1 is 2400 volts and L1 has 10 turns, then each turn of L1 will have 240 volts dropped across it. This 240 volts of magnetic induction transfers 240 volts of electricity to every turn of wire in the inner L2 coil. If the diameter of L2 is small enough to have 100 turns, then the voltage produced will be 24,000 volts. If the diameter of the L2 former allows 500 turns, then the output voltage will be 120,000 volts. 3. Choose the length and diameter of the coils. The larger the diameter of the coil, the fewer turns can be made with the wire length, and so the coil length will be less, and the output voltage will be lower. 4. For example, if 24.7 MHz is the desired output frequency, then the length of wire, in feet, would be 247 divided by 24.7, which is 10 feet of wire, 3048 mm. The coil may be wound on a standard size of PVC pipe, or alternatively, it can be purchased from a supplier, typically, an amateur radio supply store. If the voltage on each turn of L1 is arranged to be 24 volts and the desired output voltage 640 volts, then there needs to be 640/24 equal 26.66 turns on L2, wound with the 10 feet of wire already calculated. Note, at this point, Don's calculations go adrift and he suggests winding 30 turns on a 2-inch former. If you do that, then it will take about 16 feet of wire and the resonant point at 10 feet will be at about 19 turns, giving an output voltage of 458 volts instead of the required 640 volts, unless the number of turns on L1 is reduced to give more than 24 volts per turn. However, the actual required diameter of the coil former, plus 1 diameter of the wire, is 10x12/26.67 x 3.14159, equal 1.43 inches. You can make this size of former up quite easily if you want to stay with 10 turns on the L1 coil. 5. Connect to the start of the coil. To determine the exact resonant point on the coil, a measurement is made. Off-the-shelf multimeters are not responsive to high-frequency signals, so a cheap neon is used instead. Holding one wire of the neon in one hand and running the other neon wire along the outside of the L2 winding, the point of brightest light is located. Then the neon is moved along that turn to find the brightest point along that turn, and when it is located, a connection is made to the winding at that exact point. L2 is now a resonant winding. It is possible to increase the Q effectiveness of the coil by spreading the turns out a bit instead of positioning them so that each turn touches both of the adjacent turns. 6. The input power has been suggested as 2400 volts. This can be constructed from a Jacob's ladder arrangement or any step-up voltage system. An off-the-shelf module as used with lasers is another option. 7. Construction of the L1 input coil has been suggested as having 10 turns. The length of the wire in this coil is not critical. If a 2-inch diameter PVC pipe was used for the L2 coil, then the next larger size of PVC pipe can be used for the L1 coil former. Cut a 10-turn length of the pipe, probably a 3-inch diameter pipe. The pipe length will depend on the diameter of the insulated wire used to make the winding. Use a good quality multimeter or a specialized LCR meter to measure the capacitance, in farads, and the inductance, in henries, of the L2 coil. Now, put a capacitor for matching L1 to L2 across the voltage input of L1, and a spark gap connected in parallel is required for the return voltage from L1. A trimmer capacitor for L1 is desirable. 8. The performance of L2 can be further enhanced by attaching an earth connection to the base of the coil. The maximum output voltage will be between the ends of coil L2 and lesser voltages can be taken off intermediate points along the coil if that is desirable. This frequency information can be rather hard to understand in the way that Don states it. It may be easier to follow the description given by one developer who says, "I have noticed that any machine can be made a super machine just by adding a bipolar capacitor across the coil. Nothing else is needed. With the correct capacitor, the coil becomes naturally resonant and uses very little amperage. Each machine uses a different size capacitor. The correct capacitor size can be calculated by dividing the speed of light by the coil's wire length first to get the coil's natural frequency and then dividing the voltage to be used by that frequency. The result is the correct size for the capacitor. Your machine will then be very powerful even working from a 12V car battery, no other additions needed. My coil's wire length is 497.333 meters. 299 million m/sec/497.333 m equals 600,000 Hz. 12V/600,000 equals 0.00002 or 20 microfarads. A beautiful naturally resonant tank circuit. You can use this with any coil for over unity. Once we have a naturally resonant coil/capacitor combination, we can bring the frequency down to 50 Hz by calculating for the power factor correction. Hertz equal resistance x farads, then 50 Hz equal Rx 0.00002. So 50/0.00002 equal 2500000, and R equal 2500000 or 2.5 megohms. We then place all three components in parallel and our coil should give us a 50 Hz output. Don provides quite an amount of information on one of his devices shown here. Without his description of the device, it would be difficult to understand its construction and method of operation. As I understand it, the circuit of what is mounted on this board is as shown here. This arrangement has bothered some readers recently as they feel that the spark gap should be in series with the L1 coil, like this. This is understandable, as there is always a tendency to think of the spark gap as being a device which is there to protect against excessive voltages rather than seeing it as an active component of the circuit, a component which is in continuous use. In 1925, Hermann Plausen was granted a patent for a whole series of methods for converting the high voltage produced by a tall aerial system into usable, standard electricity. Hermann starts off by explaining how high voltage can be converted into a convenient form, and he uses a Wimshurst static electricity generator as an example of a constant source of high voltage. The output from a rectified Tesla coil, a Wimshurst machine and a tall aerial are very much alike, and so Hermann's comments are very relevant here. He shows it like this. Here, the output of the Wimshurst machine is stored in two high-voltage capacitors, Leyden jars, causing a very high voltage to be created across those capacitors. When the voltage is high enough, a spark jumps across the spark gap, causing a massive surge of current through the primary winding of the transformer, which in his case is a step-down transformer as he is aimed at getting a lower output voltage. Don's circuit is almost identical. Here the high voltage comes from the battery/inverter/neon tube driver/rectifiers, rather than from a mechanically driven Wimshurst machine. He has the same build-up of voltage in a capacitor with a spark gap across the capacitor. The spark gap will fire when the capacitor voltage reaches its designed level. The only difference is in the positioning of the capacitor, which if it matched Hermann's arrangement exactly, would be like this. Which would be a perfectly viable arrangement as far as I can see. You will remember that Tesla, who always speaks very highly of the energy released by the very sharp discharge produced by a spark, shows a high voltage source feeding a capacitor with the energy passing through a spark gap to the primary winding of a transformer. However, with Don's arrangement, it can be a little difficult to see why the capacitor is not short-circuited by the very low resistance of the few turns of thick wire forming the L1 coil. Well, it would do that if we were operating with DC, but we are most definitely not doing that as the output from the neon tube driver circuit is pulsing 35,000 times per second. This causes the DC resistance of the L1 coil to be of almost no consequence, and instead, the coil's impedance or reactance, effectively, its AC resistance, is what counts. Actually, the capacitor and the L1 coil being connected across each other have a combined reactance or resistance to pulsing current at this frequency. This is where the nomograph diagram comes into play, and there is a much easier to understand version of it a few pages later on in this document. So, because of the high pulsing frequency, the L1 coil does not short-circuit the capacitor, and if the pulsing frequency matches the resonant frequency of the L1 coil, or a harmonic of that frequency, then the L1 coil will actually have a very high resistance to current flow through it. This is how a crystal set radio receiver tunes in a particular radio station, broadcasting on its own frequency. Anyway, coming back to Don's device shown in the photograph above, the electrical drive is from a 12-volt battery which is not seen in the photograph. Interestingly, Don remarks that if the length of the wires connecting the battery to the inverter are exactly 1/4 of the wavelength of the frequency of the oscillating magnetic field generated by the circuit, then the current induced in the battery wires will recharge the battery continuously, even if the battery is supplying power to the circuit at the same time. The battery supplies a small current through a protecting diode, to a standard off-the-shelf true sine wave inverter. An inverter is a device which produces mains voltage alternating current from a DC battery. As Don wants adjustable voltage, he feeds the output from the inverter into a variable transformer called a variac, although this is often made as part of the neon driver circuit to allow the brightness of the neon tube to be adjusted by the user. This arrangement produces an AC output voltage which is adjustable from 0 volts up to the full mains voltage, or a little higher, though Don does not want to use a higher voltage. The use of this kind of adjustment usually makes it essential for the inverter to be a true sine wave type. As the power requirement of the neon tube driver circuit is so low, the inverter should not cost very much. The neon tube driver circuit is a standard off-the-shelf device used to drive neon tube displays for commercial establishments. The one used by Don contains an oscillator and a step-up transformer, which together produce an alternating current of 9,000 volts at a frequency of 35,100 Hz, sometimes written as 35.1 kHz. The term Hz stands for cycles per second. Don lowers the 9,000 volts as he gets great power output at lower input voltages, and the cost of the output capacitors is a significant factor. The particular neon tube driver circuit which Don is using here, has two separate outputs out of phase with each other, so Don connects them together and uses a blocking diode in each line to prevent either of them affecting the other one. Not easily seen in the photograph, the high voltage output line has a very small, encapsulated, gas discharge tube spark gap in it, and the line is also earthed. The device looks like this. Please note that when an earth connection is mentioned in connection with Don Smith's devices, we are talking about an actual wire connection to a metal object physically buried in the ground, whether it is a long copper rod driven into the ground, or an old car radiator buried in a hole like Tyrrell Copenhagen's uses. When Thomas Henry Moray performed his requested demonstration deep in the countryside at a location chosen by the skeptics, the light bulbs which formed his demonstration electrical load, glowed more brightly with each hammer stroke as a length of gas pipe was hammered into the ground to form his earth connection. It should be remarked that since Don purchased his neon tube driver module, that newer designs have generally taken over completely, especially in Europe, and these designs have built-in earth leakage current protection which instantly disables the circuit if any current is detected leaking to ground. This feature makes the unit completely unsuitable for use in a Don Smith circuit because the transfer of current to the ground is wholly intentional and vital for the operation of the circuit. The output of the neon tube driver circuit is used to drive the primary L1 winding of a Tesla coil-style transformer. This looks ever so simple and straightforward, but there are some subtle details which need to be considered. The operating frequency of 35.1 kHz is set and maintained by the neon tube driver circuitry, and so, in theory, we do not have to do any direct tuning ourselves. However, we want the resonant frequency of the L1 coil and the capacitor across it to match the neon driver circuit frequency. The frequency of the L1 coil winding will induce exactly the same frequency in the L2 secondary winding. However, we need to pay special attention to the ratio of the wire lengths of the two coil windings, as we want these two windings to resonate together. A rule of thumb followed by most Tesla coil builders is to have the same weight of copper in the L1 and L2 coils, which means that the wire of the L1 coil is usually much thicker than the wire of the L2 coil. If the L1 coil is to be 1/4 of the length of the L2 coil, then we would expect the cross-sectional area of the L1 coil to be 4 times that of the wire of the L2 coil, and so the wire should have twice the diameter, as the area is proportional to the square of the radius, and the square of 2 is 4. Don uses a white plastic tube as the former for his L1 primary coil winding. As you can see here, the wire is fed into the former, leaving sufficient clearance to allow the former to slide all the way into the outer coil. The wire is fed up inside the pipe and out through another hole to allow the coil turns to be made on the outside of the pipe. There appear to be 5 turns, but Don does not always go for a complete number of turns, so it might be 4.3 turns or some other value. The key point here is that the length of wire in the L1 coil turns should be exactly 1/4 of the length of wire in the L2 coil turns. The L2 coil used here is a commercial 3-inch diameter unit from Barker & Williamson, constructed from uninsulated, solid, single-strand tinned copper wire. How to make home-build versions is shown later on. Don has taken this coil and unwound 4 turns in the middle of the coil in order to make a center tap. He then measured the exact length of wire in the remaining section and made the length of the L1 coil turns to be exactly 1/4 of that length. The wire used for the L1 coil looks like Don's favorite jumbo speaker wire, which is a very flexible wire with a very large number of extremely fine uninsulated copper wires inside it. You will notice that Don has placed a plastic collar on each side of the winding, matching the thickness of the wire, in order to create a secure sliding operation inside the outer L2 coil, and the additional plastic collars positioned further along the pipe provide further support for the inner coil. This sliding action allows the primary coil L1 to be positioned at any point along the length of the L2 secondary coil, and that has a marked tuning effect on the operation of the system. The outer L2 coil does not have any kind of tube support, but instead, the coil shape is maintained by the stiffness of the solid wire plus 4 slotted strips. This style of construction produces the highest possible coil performance at radio frequencies. With a Tesla coil, it is most unusual to have the L1 coil of smaller diameter than the L2 coil. The L2 coil has 2 separate sections, each of 17 turns. One point to note is the turns are spaced apart using slotted strips to support the wires and maintain an accurate spacing between adjacent turns. It must be remembered that spacing coil turns apart like this alters the characteristics of the coil, increasing its capacitance factor substantially. Every coil has resistance, inductance and capacitance, but the form of the coil construction has a major effect on the ratio of these 3 characteristics. The coil assembly is held in position on the baseboard by 2 off-white plastic cable ties. The nearer half of the coil is effectively connected across the further half as shown in the circuit diagram above. One point which Don stresses, is that the length of the wire in the L1 coil and the length of wire in the L2 coil, must be an exact even division or multiple of each other. In this case, the L2 wire length in each half of the L2 coil is exactly 4 times as long as the L1 coil wire length. This is likely to cause the L1 coil to have part of a turn, due to the different coil diameters. For example, if the length of the L2 coil wire is 160 inches and L1 is to be 1/4 of that length, namely, 40 inches. Then, if the L1 coil has an effective diameter of 2.25 inches, allowing for the thickness of the wire when wound on a 2-inch diameter former, then the L1 coil would have 5.65, or 5 2/3, turns, which causes the finishing turn of L2 to be 240 degrees further around the coil former than the start of the first turn, that is, 5 full turns plus 2/3 of the 6th turn. The L1/L2 coil arrangement is a Tesla coil. The positioning of the L1 coil along the length of the L2 coil adjusts the voltage to current ratio produced by the coil. When the L1 coil is near the middle of the L2 coil, then the amplified voltage and amplified current are roughly the same. The exact wire ratio of these 2 coils gives them an almost automatic tuning with each other, and the exact resonance between them can be achieved by the positioning of the L1 coil along the length of the L2 coil. While this is a perfectly good way of adjusting the circuit, in the build shown in the photograph, Don has opted to get the exact tuning by connecting a capacitor across L1 as marked as C in the circuit diagram. Don found that the appropriate capacitor value was around the 0.1 microfarad, 100 nanofarads, mark. It must be remembered that the voltage across L1 is very high, so if a capacitor is used in that position it will need a voltage rating of at least 9000 volts. Don remarks that the actual capacitors seen in the photograph of this prototype are rated at 15,000 volts, and were custom made for him using a self-healing style of construction. As has already been remarked, this capacitor is an optional component. Don also opted to connect a small capacitor across the L2 coil, also for fine-tuning of the circuit, and that component is optional and so is not shown on the circuit diagram. As the two halves of the L2 coil are effectively connected across each other, it is only necessary to have one fine-tuning capacitor. However, Don stresses that the height length of the coil, when standing vertically, controls the voltage produced while the coil width, the diameter of the turns, controls the current produced. The exact wire length ratio of the turns in the L1 and L2 coils gives them an almost automatic synchronous tuning with each other, and the exact resonance between them can be achieved by the positioning of the L1 coil along the length of the L2 coil. While this is a perfectly good way of adjusting the circuit, in the 1994 build shown in the photograph, Don has opted to get the exact tuning by connecting a capacitor across L1 as marked as C in the circuit diagram. Don found that the appropriate capacitor value for his particular coil build was about 0.1 microfarad, 100 NF, and so he connected two 47 NF high voltage capacitors in parallel to get the value which he wanted. It must be remembered that the voltage across L1 is very high, so a capacitor used in that position needs a voltage rating of at least 9000 volts. Don remarks that the actual capacitors seen in the photograph of this prototype are rated at 15,000 volts, and were custom made for him using a self-healing style of construction. Don has also connected a small capacitor across the L2 coil, and that optional component is marked as C2 in the circuit diagram, and the value used by Don happened to be a single 47 NF, high voltage capacitor. As the two halves of the L2 coil are effectively connected across each other, it is only necessary to have one capacitor for L2. There are various ways of dealing with the output from the L2 coil in order to get large amounts of conventional electrical power out of the device. The method shown here uses the four very large capacitors seen in the photograph. These have an 8000 or 9000 volt rating and a large capacity, and they are used to store the circuit power as DC prior to use in the load equipment. This is achieved by feeding the capacitor bank through a diode, which is rated for both high voltage and high current, as Don states that the device produces 8000 volts at 20 amps, in which case, this rectifying diode has to be able to handle that level of power, both at startup when the capacitor bank is fully discharged and L2 is producing 8000 volts, and when the full load of 20 amps is being drawn. This capacitor bank is fed through a diode which is rated for both high voltage and high current, as Don states that the device produces 8000 volts at 20 amps, in which case, this rectifying diode has to be able to handle that level of power, both at startup when the capacitor bank is fully discharged and L2 is producing 8000 volts, and when the full load of 20 amps is being drawn. The actual diodes used by Don happen to be rated at 25 kV, but that is a far greater rating than is actually needed. In passing, it might be remarked that the average home user will not have an electrical requirement of anything remotely like as large as this, seeing that 10 kW is more than most people use on a continuous basis, while 8 kV at 20A is a power of 160 kW. As the neon tube driver circuit can put out 9000 volts, and since the L1/L2 coil system is a step-up transformer, if the voltage fed to the capacitor bank is to be kept down to 8000 volts, then the variac adjustment must be used to reduce the voltage fed to the neon tube driver circuit, In order to lower the voltage fed to the L1/L2 coil pair, typically, to 3000 volts. A very astute and knowledgeable member of the EVGRAY Yahoo EVGRAY forum, whose ID is SilverHealthEU, has recently pointed out that Don Smith says quite freely that he does not disclose all of the details of his designs, and it is his opinion that a major item which has not been disclosed is that the diodes in the circuit diagrams shown here are the wrong way round, and that Don operates his voltages in reverse to the conventional way. In fact, the circuit diagram should be. He comments, the diodes leaving the neon tube driver may need to be reversed as we want to collect the negative polarity. The spark gap will then operate on ambient inversion, and the spark will look and sound totally different, with a much faster crack and producing very little heat, and even becoming covered in frost is possible. The variac should be raised up just enough to get a spark going, then backed off slightly. Any higher voltage is liable to make the neon tube driver think that it has a short circuit condition, and the new electronic designs will then shut down automatically and fail to operate at all if this method is not followed. When running, C, L1 and L2 operate somewhere up in the radio frequency band because the neon tube driver only acts as a tank circuit exciter. The large collection capacitor C3 should fill inverted to earth polarity as shown above. The load will then be pulling electrons from the earth as the cap is refilled back to zero, rather than the joules in the capacitor being depleted. Also remember that the back EMF systems of John Bedini and others create a small positive pulse, but they collect a super large negative polarity spike which shoots off the bottom of an oscilloscope display. This is what we want, plenty of this stored in capacitors, and then let the ambient background energy supply the current when it makes the correction. This is a very important point, and it may well make a really major difference to the performance of a device of this nature. One reader has drawn attention to the fact that Don's main document indicates that there should be a resistor R across the L1 coil as well as the capacitor C, and he suggests that the circuit should actually be as shown above, considering what Don said earlier about his suitcase design. Another reader points out that the wire in the output choke shown in the photograph below appears to be wound with wire that is far too small diameter to carry the currents mentioned by Don. It seems likely that a choke is not needed in that position except to suppress possible radio frequency transmissions from the circuit, but a more powerful choke can easily be wound using larger diameter wire. When the circuit is running, the storage capacitor bank behaves like an 8000-volt battery which never runs down and which can supply 20 amps of current for as long as you want. The circuitry for producing a 220-volt 50 Hz AC output or a 110-volt 60 Hz AC output from the storage capacitors is just standard electronics. In passing, one option for charging the battery is to use the magnetic field caused by drawing mains frequency current pulses through the output choke coil, shown here. The output current flows through the left-hand winding on the brown cylindrical former, and when the photograph was taken, the right-hand winding was no longer in use. Previously, it had been used to provide charging power to the battery by rectifying the electrical power in the coil, caused by the fluctuating magnetic field caused by the pulsing current flowing through the left-hand winding, as shown here. The DC output produced by the 4 diodes was then used to charge the driving battery, and the power level produced is substantially greater than the minor current drain from the battery. Consequently, it is a sensible precaution to pass this current to the battery via a circuit which prevents the battery voltage rising higher than it should. A simple voltage level sensor can be used to switch off the charging when the battery has reached its optimum level. Other batteries can also be charged if that is wanted. Simple circuitry of the type shown in Chapter 12 can be used for controlling and limiting the charging process. The components on Don's board are laid out like this. Don draws attention to the fact that the cables used to connect the output of L2 to the output of the board, connecting the storage capacitors on the way, are very high voltage rated cables with special multiple coverings, to ensure that the cables will remain sound over an indefinite period. It should be remarked at this point, that the outer 3 diameter coil used by Don is not wound on a former, but in order to get higher performance at high frequencies, The turns are supported with 4 separate strips physically attached to the turns, the technique described later in this document as being an excellent way for home construction of such coils. Please bear in mind that the voltages here and their associated power levels are literally lethal and perfectly capable of killing anyone who handles the device carelessly when it is powered up. When a replication of this device is ready for routine use, it must be encased so that none of the high voltage connections can be touched by anyone. This is not a suggestion, but it is a mandatory requirement, despite the fact that the components shown in the photographs are laid out in what would be a most dangerous fashion were the circuit to be powered up as it stands. Under no circumstances, construct and test the circuit unless you are already experienced in the use of high voltage circuits or can be supervised by somebody who is experienced in this field. This is a one hand in the pocket at all times type of circuit, and it needs to be treated with great care and respect at all times, so be sensible. The remainder of the circuit is not mounted on the board, possibly because there are various ways in which the required end result can be achieved. The one suggested here is perhaps the most simple solution. The voltage has to be dropped, so an iron cord mains frequency step-down transformer is used to do this. To get the frequency to the standard mains frequency for the country in which the device is to be used, an oscillator is used to generate that particular mains frequency. The oscillator output is used to drive a suitable high-voltage semiconductor device, be it an FET transistor, an IGBT device, or whatever. This device has to switch the working current at 8000 volts, though admittedly, that will be a current which will be at least 36 times lower than the final output current, due to the higher voltage on the primary winding of the transformer. The available power will be limited by the current handling capabilities of this output transformer, which needs to be very large and expensive. As the circuit is capable of picking up additional magnetic pulses, such as those generated by other equipment, nearby lightning strikes, etc., an electronic component called a varistor marked V in the diagram, is connected across the load. This device acts as a voltage spike suppressor as it short-circuits any voltage above its design voltage, protecting the load from power surges. Don also explains an even more simple version of the circuit as shown here. This simplified circuit avoids the need for expensive capacitors and the constraints of their voltage ratings, and the need for electronic control of the output frequency. The wire length in the turns of coil L2 still needs to be exactly 4 times the wire length of the turns in coil L1, but there is only one component which needs to be introduced, and that is the resistor R placed across the primary winding of the step-down isolation transformer. This transformer is a laminated iron core type, suitable for the low mains frequency, but the output from L2 is at much higher frequency. It is possible to pull the frequency down to suit the step-down transformer by connecting the correct value of resistor R across the output transformer, or a coil and resistor, or a coil and a capacitor. The value of resistor needed can be predicted from the American Radio Relay League graph, shown as Fig 44 in Don's PDF document, which can be downloaded using http://www.free-energy-info.com/smith.pdf right parenthesis. The 6th edition of the Howard Sams Book Handbook of Electronics Tables and Formulas, ISBN 10-0672224690 or ISBN 13-978-0672224690, has a table which goes down to 1 kHz and so does not need to be extended to reach the frequencies used here. The correct resistor value could also be found by experimentation. You will notice that an earthed dual spark gap has been placed across L2 in order to make sure that the voltage levels always stay within the design range. Don also explains an even more simple version which does not need a variac, high voltage capacitors or high voltage diodes. Here, a DC output is accepted, which means that high frequency step-down transformer operation can be used. This calls for an air core transformer which you would wind yourself from heavy-duty wire. Mains loads would then be powered by using a standard off-the-shelf inverter. In this version, it is of course necessary to make the L1 turns wire length exactly 1/4 of the L2 turns wire length in order to make the two coils resonate together. The operating frequency of each of these coils is imposed on them by the output frequency of the neon tube driver circuit. That frequency is maintained throughout the entire circuit until it is rectified by the 4 diodes feeding the low voltage storage capacitor. The target output voltage will be either just over 12 volts or just over 24 volts, depending on the voltage rating of the inverter which is to be driven by the system. The circuit diagram is. As many people will find the nomograph chart in Don's PDF document very difficult to understand and use, here is an easier version. The objective here is to determine the reactance or AC resistance in ohms, and the way to do that is as follows. Suppose that your neon tube driver is running at 30 kHz and you are using a capacitor of 100 nanofarads, which is the same as 0.1 microfarad, and you want to know what is the AC resistance of your capacitor is at that frequency. Also, what coil inductance would have that same AC resistance. Then the procedure for finding that out is as follows. Draw a straight line from your 30 kHz frequency, purple line, through your 100 nanofarad capacitor value and carry the line on as far as the blue inductance line as shown above. You can now read the reactance, AC resistance, off the red line, which looks like 51 ohms to me. This means that when the circuit is running at a frequency of 30 kHz, then the current flow through your 100 NF capacitor will be the same as through a 51 ohm resistor. Reading off the blue inductance line, that same current flow at that frequency would occur with a coil which has an inductance of 0.28 millihenries. I have recently been passed a copy of Don's circuit diagram for this device, and it is shown here. The 4000 volt 30 milliamp transformer shown in this circuit diagram may use a ferrite cord transformer from a neon tube driver module which steps up the voltage, but it does not raise the frequency, as that is clearly marked at 120 Hz pulse DC. You will notice that the circuit diagram is drawn with plus shown below minus, which is most unusual. Please note that when an earth connection is mentioned in connection with Don Smith's devices, we are talking about an actual wire connection to a metal object physically buried in the ground, whether it is a long copper rod driven into the ground, or an old car radiator buried in a hole like Tyrrell Copenads used, or a buried metal plate. When Thomas Henry Moray performed his requested demonstration deep in the countryside at a location chosen by the skeptics, the light bulbs which formed his demonstration electrical load, glowed more brightly with each hammer stroke as a length of gas pipe was hammered into the ground to form his earth connection. Don also explains an even more simple version of his main device. This version does not need a variable voltage transformer, or high voltage capacitors. Here, a DC output is accepted, which means that high frequency step-down transformer operation can be used. This calls on the output side, for an air core, or ferrite rod core transformer which you would wind yourself from heavy-duty wire. Mains loads would then be powered by using a standard off-the-shelf inverter. In this version, it is of course, very helpful to make the L1 turns wire length exactly 1/4 of the L2 turns wire length in order to make the two coils automatically resonate together. The operating frequency of each of these coils is imposed on them by the output frequency of the neon tube driver circuit. That frequency is maintained throughout the entire circuit until it is rectified by the 4 diodes feeding the low voltage storage capacitor. The target output voltage will be either just over 12 volts or just over 24 volts, depending on the voltage rating of the inverter which is to be driven by the system. As the circuit is capable of picking up additional magnetic pulses, such as those generated by other equipment, nearby lightning strikes, etc., an electronic component called a varistor marked V in the diagram, is connected across the load. This device acts as a voltage spike suppressor as it short circuits any voltage above its design voltage, protecting the load from power surges. A gas discharge tube is an effective alternative to a varistor. This circuit is effectively 2 Tesla coils back to back, and the circuit diagram might be. It is by no means certain that in this circuit, the red and blue windings are wound in opposing directions. The spark gap, or gas discharge tube, in series with the primary of the first transformer alters the operation in a somewhat unpredictable way, as it causes the primary to oscillate at a frequency determined by its inductance and its self-capacitance, and that may result in megahertz frequencies. The secondary winding, S, of that transformer must resonate with the primary, and in the circuit which has no frequency compensating capacitors, that resonance is being produced by the exact wire length in the turns of the secondary. This looks like a simple circuit, but it is anything but that. The excess energy is produced by the raised frequency, the raised voltage, and the very sharp pulsing produced by the spark. That part is straightforward. The remainder of the circuit is likely to be very difficult to get resonating, as it needs to be in order to deliver that excess energy to the output inverter. When considering the length of wire in a resonant coil, it is necessary to pay attention to the standing wave created under those conditions. The wave is caused by reflection of the signal when it reaches the end of the wire, or when there is a sudden change in the diameter of the wire, as that changes the signal reflection ability at that point in the connection. You should pay attention to Richard Quick's very clear description of this in the section of his patent which is included later on in this chapter. Also, remember what Don Smith said about locating the peaks of the standing wave by using a handheld neon lamp. One very significant thing which Don pointed out is that the mains electricity available through the wall socket in my home does not come along the wires from the generating station. Instead, the power station influences a local substation, and the electrons which flow through my equipment actually come from my local environment because of the influence of my local substation. Therefore, if I can create a similar influence in my home, then I no longer need that substation and can have as much electrical energy as I want, without having to pay somebody else to provide that influence for me. A practical implementation of one of Don Smith's designs. The objective here is to determine how to construct a self-powered, free energy electrical generator which has no moving parts, is not too expensive to build, uses readily available parts, and which has an output of some kilowatts. However, under no circumstances should this document be considered to be an encouragement for you, or anyone else, to actually build one of these devices. This document is presented solely for information and educational purposes, and as high voltages are involved, it should be considered to be a dangerous device unsuited to being built by inexperienced amateurs. The following section is just my opinions and so should not be taken as tried and tested, working technology, but instead, just the opinion of an inexperienced writer. However, questions from several different readers indicate that a short, reasonably specific description of the steps needed to attempt a replication of a Don Smith device would be helpful. Again, this document must not be considered to be a recommendation that you actually build one of these high-voltage, potentially dangerous devices. This is just information intended to help you understand what I believe is involved in this process. In broad outline, the following steps are used in the most simple version of the arrangement. 1. The very low frequency and voltage of the local main supply is discarded in favor of an electrical supply which operates at more than 20,000 Hz, cycles per second, and has a voltage of anything from 350 volts to 10,000 volts. The higher voltages can give greater overall output power, but they involve greater effort in getting the voltage back down again to the level of the local mains voltage in order for standard mains equipment to be used. 2. This high-frequency high voltage is used to create a series of very rapid sparks using a spark gap which is connected to a ground connection. Properly done, the spark frequency is so high that there is no audible sound caused by the sparks. Each spark causes a flow of energy from the local environment into the circuit. This energy is not standard electricity which makes things hot when current flows through them, but instead this energy flow causes things to become cold when the power flows through them, and so it is often called cold electricity. It is tricky to use this energy unless all you want to do is light up a series of light bulbs, which incidentally, give out a different quality of light when powered with this energy. Surprisingly, the circuit now contains substantially more power than the amount of power needed to produce the sparks. This is because additional energy flows in from the ground as well as from the local environment. If you have conventional training and have been fed the myth of closed systems, then this will seem impossible to you. So, let me ask you the question, if, as can be shown, all of the electricity flowing into the primary winding of a transformer, flows back out of that winding, then where does the massive, continuous flow of electricity coming from the secondary winding come from? None of it comes from the primary circuit, and yet millions of electrons flow out of the secondary in a continuous stream which can be supplied indefinitely. So, where do these electrons come from? The answer is from the surrounding local environment, which is seething with excess energy, but your textbooks won't like that fact, as they believe that the transformer circuit is a closed system, something which probably can't be found anywhere in this universe. 3. This high voltage, high frequency, high power energy needs to be converted to the same sort of hot electricity which comes out of a mains wall socket at the local voltage and frequency. This is where skill and understanding come into play. The first step is to lower the voltage and increase the available current with a step-down resonant transformer. This sounds highly technical and complicated, and looking at Don Smith's expensive Barker and Williamson coil, makes the whole operation appear to be one for rich experimenters only. This is not the case, and a working solution can be cheap and easy. It is generally not convenient to get the very high voltage all the way down to convenient levels in a single step, and so, one or more of those resonant transformers can be used to reach the target voltage level. Each step-down transformer boosts the available current higher and higher. 4. When a satisfactory voltage has been reached, we need to deal with the very high frequency. The easiest way to deal with it is to use high-speed diodes to convert it to pulsing DC and feed that into a capacitor to create what is essentially an everlasting battery. Feeding this energy into a capacitor converts it into conventional hot electricity, and a standard off-the-shelf inverter can be used to give the exact voltage and frequency of the local mains supply. In most of the world, that is 220 volts at 50 cycles per second. In America it is 110 volts at 60 cycles per second. Low-cost inverters generally run on either 12 volts or 24 volts, with the more common 12-volt units being cheaper. So, let's take a look at each of these steps in more detail and see if we can understand what is involved and what our options are. 1. We want to produce a high voltage, high frequency, low current power source. Don Smith shows a neon sign transformer module. His module produced a voltage which was higher than was convenient, and so he used a variable AC transformer, or variac as it is commonly known, to lower the input voltage and so lower the output voltage. There is actually no need for a variac, as we can handle the higher voltage, or alternatively, use a more suitable neon sign transformer module. However, we have a problem with using that technique. In the years since Don bought his module, they have been redesigned to include circuitry which disables the module if any current flows out of it directly to earth, and as that is exactly what we would want to use it for, so most, if not all, of the currently available neon sign transformer modules are not suitable for our needs. However, I'm told that if the module has an earth wire and that earth wire is left unconnected, that it disables the earth leakage circuitry, allowing the unit to be used in a Don Smith circuit. Personally, I would not recommend that if the module is enclosed in a metal housing. A much cheaper alternative is shown here. http://www.youtube.com/watch?v=rho_4d93q, where a small plasma globe circuit is used to generate a high frequency spark. It seems highly likely that one of those modules would suit our needs. An alternative method is to build your own power supply from scratch. Doing that is not particularly difficult, and if you do not understand any electronics, then perhaps reading the beginner's electronics tutorial in chapter 12. http://www.free-energy-info.com/chapter12.pdf right parenthesis will fill you in on all of the basics needed for understanding, and probably designing your own circuits of this type. Here is a variable frequency design for home construction. One advantage of this circuit is that the output transformer is driven at the frequency set by the 555 timer, and that frequency is not affected by the number of turns in the primary winding, nor its inductance, wire diameter, or anything else to do with the coil. While this circuit shows the rather expensive IRF9130 transistor, I expect that other P-channel FETs would work satisfactorily in this circuit. The IRF9130 transistor looks like this. The circuit has a power supply diode and capacitor, ready to receive energy from the output at some later date if that is possible and desired. The 555 circuit is standard, giving a 50% mark space ratio. The 10 nanofarad capacitor is there to maintain the stability of the 555, and the timing section consists of two variable resistors, one fixed resistor and the 1 nanofarad capacitor. This resistor arrangement gives a variable resistance of anything from 100 ohms to 51.8K, and that allows a substantial frequency range. The 47K, linear, variable resistor controls the main tuning, and the 4.7 kilo, linear, variable resistor gives a more easily adjustable frequency for exact tuning. The 100 ohm resistor is there in case both of the variable resistors are set to zero resistance. The output is fed through a 470 ohm resistor to the gate of a very powerful P-channel FET transistor, which drives the primary winding of the output transformer. The output transformer can be wound on an insulating spool covering a ferrite rod, giving both good coupling between the windings, and high frequency operation as well. The turns ratio is set to just 30:1 due to the high number of primary winding turns. With a 12-volt supply, this will give a 360-volt output waveform, and by reducing the primary turns progressively, allows the output voltage to be increased in controlled steps. With 10 turns in the primary, the output voltage should be 3600 volts, and with just 5 turns 7200 volts. The higher the voltage used, the greater the amount of work needed later on to get the voltage back down to the output level which we want. Looking at the wire specification table, indicates that quite a small wire diameter could be used for the oscillator output transformer's secondary winding. While this is perfectly true, it is not the whole story. Neon tube drivers are very small, and the wire in their output windings is very small diameter indeed. Those driver modules are very prone to failure. If the insulation on any one turn of the winding fails and one turn becomes a short circuit, then that stops the winding from oscillating, and a replacement is needed. As there are no particular size constraints for this project, it might be a good idea to use enameled copper wire of 0.45 mm or larger in an attempt to avoid this insulation failure hazard. No part of the transformer coil spool should be metal, and it would not be any harm to cover each layer of secondary winding with a layer of electrical tape to provide additional insulation between the coil turns in one layer and the turns in the layer on top of it. A plug-in board layout might be. Please remember that you can't just stick your average voltmeter across a 4 kV capacitor, unless you really do want to buy another meter, as they only measure up to about 1000 volts DC. So, if you are using high voltage, then you need to use a resistor divider pair and measure the voltage on the lower resistor. But what resistor values should you use? If you put a 10 megohm resistor across your 4 kV charged capacitor, the current flowing through the resistor would be 0.4 milliamps. Sounds tiny, doesn't it? But that 0.4 milliamp is 1.6 watts, which is a good deal more than the wattage which your resistor can handle. Even using this arrangement, the current will be 0.08 milliamps and the wattage per resistor will be 64 milliwatts. The meter reading will be about 20% of the capacitor voltage, which will give a voltmeter reading of 800 volts. The input resistance of the meter needs to be checked and possibly allowed for, as the resistance in this circuit is so high, see Chapter 12. When making a measurement of this type, the capacitor is discharged, the resistor chain and meter attached, and then, and only then, Is the circuit powered up, the reading taken, the input power disconnected, the capacitor discharged, and the resistors disconnected? High voltage circuits are highly dangerous, especially so, where a capacitor is involved. The recommendation to wear thick rubber gloves for this kind of work is not intended to be humorous. Circuits of this type are liable to generate unexpected high voltage spikes, and so, it might be a good idea to connect a varistor across the meter to protect it from those spikes. The varistor need to be set to the voltage which you intend to measure, and as varistors may not be available above a 300V threshold, 2 or more may need to be connected in series where just one is shown in the diagram above. The varistor should not have a higher voltage rating than your meter. 2. We now need to use this high voltage to create a strategically positioned spark to a ground connection. When making an earth connection, it is sometimes suggested that connecting to water pipes or radiators is a good idea, as they have long lengths of metal piping running under the ground and making excellent contact with it. However, it has become very common for metal piping to be replaced with cheaper plastic piping, and so any proposed pipe connection needs a check to ensure that there is metal piping which runs all the way into the ground. The spark gaps shown can be commercial high voltage gas discharge tubes, adjustable homemade spark gaps with stainless steel tips about 1 mm apart, car spark plugs, or standard neon bulbs, although these run rather hot in this application. A 15mm x 6mm size neon bulb operates with only 90 or 100 volts across it. It would take a considerable number of them connected in series to create a high voltage spark gap, but it is probably a misconception that the spark gap itself needs a high voltage. Later on in this chapter, there is an example of a very successful system where just one neon bulb is used for the spark gap, and an oscillating magnetic field more than a meter wide is created when driven by just an old 2500 volt neon sign transformer module. If using a neon bulb for the spark gap, then an experienced developer recommends that a 22K resistor is used in series with the neon in order to extend its working life very considerably. This circuit is one way to connect the spark gap and ground connection. This is an adaptation of a circuit arrangement used by the forum member Slow and Easy on the Don Smith topic in the Energetic Forum. Here, he is using a low-glow neon transformer intended for use on a bicycle. The diodes are there to protect the high-voltage power supply from any unexpected voltage spikes created later on in the circuit. The spark gap is connected between the primary winding of a step-up transformer and the earth connection. No capacitor is used. Seeing this circuit, we immediately think of Don Smith's large and expensive coils, but this experimenter does not use anything like that. Instead, he winds his transformer on a simple plastic former like this. And to make matters worse, the primary winding wire is just 9 inches, 228.6 mm, long, and the secondary just 36 inches, 914.4 mm, long, the primary being wound directly on top of the secondary. Not exactly a large or expensive construction, and yet one which appears to perform adequately in actual tests. This is a very compact form of construction, but there is no necessity to use exactly the same former for coils, nor is there anything magic about the 9-inch length of the L1 coil, as it could easily be any convenient length, say 2 feet or 0.5 meters, or whatever. The important thing is to make the L2 wire length exactly 4 times that length, cutting the lengths accurately. It is common practice to match the weight of copper in each coil, and so the shorter wire is usually twice the diameter of the longer wire. The circuit above produces a cold electricity output of high voltage and high frequency. The voltage will not be the same as the neon transformer voltage, nor is the frequency the same either. The two coils resonate at their own natural frequency, unaltered by any capacitors. 3. The next step is to get the high voltage down to a more convenient level, perhaps, like this. Here, an identical transformer, wound in exactly the same way, is used in reverse, to start the voltage lowering sequence. The wire length ratio is maintained to keep the transformer windings resonant with each other. Supposing we were to wind the L2 coil of this second transformer in a single straight winding, and instead of winding just one L1 winding on top of it, two or more L1 identical windings were placed on top of it, what would happen? Now for a comment which will seem heretical to people steeped in the present day, inadequate, level of technology. The power flowing in these transformers is cold electricity, which operates in an entirely different way to hot electricity. The coupling between these coils would be inductive if they were carrying hot electricity, and in that case, any additional power take off from additional L1 coils would have to be paid for by additional current draw through the L2 coil. However, with the cold electricity which these coils are actually carrying, the coupling between the coils is magnetic and not inductive, and that results in no increase in L2 current, no matter how many L1 coil take-offs there are. Any additional L1 coils will be powered for free. However, the position of the coils relative to each other has an effect on the tuning, so the L1 coil should be in the middle of the L2 coil, which means that any additional L1 coils are going to be slightly off the optimum tuning point. 4. Anyway, following through on just one L1 coil, there is likely to be at least one further step-down transformer needed, and eventually, we need conversion to hot electricity. Probably the easiest conversion is by feeding the energy into a capacitor and making it standard DC. The frequency is still very high, so high-speed diodes, such as the 75 nanosecond UF54008, are needed here, although the voltage level is now low enough to be no problem. The DC output can be used to power an inverter so that standard mains equipment can be used. It is not necessary to use just one, expensive, large capacity inverter to power all possible loads, as it is cheaper to have several smaller inverters, each powering its own set of equipment. Most equipment will run satisfactorily on square wave inverters, and that includes a mains unit for powering the input oscillator circuit. PVC pipe is not a great material when using high-frequency high-voltage signals, and gray PVC pipe is a particularly poor coil former material. The much more expensive acrylic pipe is excellent, but if using PVC, then performance will be better if the PVC pipe is coated with an insulating lacquer, or table tennis balls dissolved in acetone as shown on YouTube. However, there are some other factors which have not been mentioned. For example, if the L1 coil is wound directly on top of the L2 coil, it will have roughly the same diameter, and so, the wire being 4 times longer, will have roughly 4 times as many turns, giving a step-up or step-down ratio of around 4:1. If, on the other hand, the coil diameters were different, the ratio would be different, as the wire lengths are fixed relative to each other. If the L2 coil were half the diameter of the L1 coil, then the turns ratio would be about 8:1, and at 1/3 diameter, 12:1, and at a quarter diameter 16:1, which means that a much greater effect could be had from the same wire length by reducing the L2 coil diameter. However, the magnetic effect produced by a coil is linked to the cross-sectional area of the coil, and so a small diameter is not necessarily at great advantage. Also, the length of the L1 coil wire and number of turns in it affect the DC resistance, and more importantly, the AC impedance, which affects the amount of power needed to pulse the coil. It is also thought that having the same weight of copper in each winding gives an improved performance, but what is not often mentioned is the opinion that the greater the weight of copper, the greater the effect. You will recall that Joseph Newman, Chapter 11, uses large amounts of copper wire to produce remarkable effects. So, while 9 inches and 36 inches of wire will work for L1 and L2, there may well be improved performance from longer lengths of wire and or thicker wires. We should also not forget that Don Smith pointed out that voltage and current act out of phase and in opposite directions along the L2 coil, moving away from the L1 coil. It has been suggested that a greater and more effective power output can be obtained by splitting the L2 coil underneath the L1 coil position, winding the second part of L2 in the opposite direction and grounding the junction of the two L2 windings. Don doesn't consider it necessary to reverse the direction of winding. The result is an L2 winding which is twice as long as before and arranged like this. Here, the additional high voltage diodes allow the two out-of-phase windings to be connected across each other. You will notice that this arrangement calls for two separate earth connections, both of which need to be high-quality connections, something like a pipe or rod driven deeply into moist soil, or alternatively, a metal plate or similar metal object of substantial surface area, buried deep in moist earth, and a thick copper wire or copper braid used to make the connection. These earthing points need to be fairly far apart, say, 10 meters. A single earth connection can't be used, as that would effectively short-circuit across the L1/L2 transformer, which you really do not want to do. With this arrangement, the outline circuit becomes. The thick earth wiring is helpful because in order to avoid the earth wire being included in the resonant wire length, you need a sudden change in wire cross-section. These are just some ideas which might be considered by some experienced developer who may be thinking of investigating Don Smith-style circuitry. To give you some idea of the capacity of some commercially available wires when carrying hot electricity, this table may help. It is recommended that the wire have a current carrying capacity of 20% more than the expected actual load, so that it does not get very hot when in use. The wire diameters do not include the insulation, although for solid enameled copper wire, that can be ignored. There is a most impressive video and circuit shown at http://utuesday.be/q3vr6qmolw, where a very simple arrangement produces an immediately successful performance for the front end of Don's circuitry. The circuit appears to be, here, a simple neon sign transformer module which has no earth connection, is used to produce a 2.5 kV voltage with a frequency of 25 kHz and a maximum output current capacity of 12 mA. There is no difficulty in constructing the equivalent to that power supply unit. The two outputs from the module are converted to DC by a chain of 41N4007 diodes in series in each of the two outputs, each chain being inside a plastic tube for insulation. This output is fed through an optional 22K resistor via a neon lamp to a microwave oven capacitor, which happens to be 874 nanofarads with a voltage rating of 2100 volts. You might feel that the voltage rating of the capacitor is too low for the output voltage of the neon sign module, but the neon has a striking voltage of just 90 volts, and so the capacitor is not going to reach the output voltage of the power supply. The resistors are solely to extend the life of the neons, as the gas inside the tube gets a considerable jolt in the first nanosecond after switch on. It is unlikely that omitting those resistors would have any significant effect, but then, including them is a trivial matter. The second neon feeds the primary of the resonant transformer, which is only shown in notional outline in the diagram above, as the developer suggests that the primary acts as a transmitter and that any number of receiving coils can be used as individual secondaries by being tuned to the exact frequency of that resonating primary. In the video showing this arrangement, the developer demonstrates the fluctuating, high-frequency field which extends for some 4 feet, 1.2 m, around the coil. He also remarks that the single neons in his arrangement could each be replaced with 2 neons in series. In test which I ran, I found that I needed 2 neons in series ahead of the capacitor in order to get continuous lighting of the output neon. Also, one of the diodes needed to be reversed so that one faced towards the input and one away from it. It did not matter which diode was reversed, as both configurations worked. Again, please note that this presentation is for information purposes only, and it is not a recommendation that you should actually build one of these devices. Let me stress again that this is a high-voltage device made even more dangerous by the inclusion of a capacitor, and it is quite capable of killing you, so, don't build one. The developer suggests that it is an implementation of the transmitter section of Don's transmitter/multiple receivers design shown below. However, before looking at that design, there is one question which causes a good deal of discussion on the forums, namely, if the center tap of the L2 secondary coil is connected to ground, then should that earth connection wire length be considered to be part of the quarter length of the L1 coil? To examine this possibility in depth, The following quote from Richard Quick's very clear explanation of resonance in his U.S. patent 7,973,296 of July 5, 2011 is very helpful. However, the simple answer is that for there to be exact resonance between two lengths of wire, whether or not part, or all of those lengths of wire happen to be wound into a coil, then one length needs to be exactly 4 times as long as the other, and ideally, half the diameter as well. At both ends of both lengths of wire, there needs to be a sudden change in wire diameter, and Richard explains why this is. But, leaving that detailed explanation for now, we can use that knowledge to explain the above simplified system in more detail. Here is the circuit again. One very important point to note is that no earth connection is required, and in spite of that, the performance shown on video is very impressive. While an earth connection can feed substantial power into the circuit, not needing one for the front end is an enormous advantage and potentially opens the way for a truly portable device. Another very important point is the utter simplicity of the arrangement, where only cheap, readily available components are used, and not many of those are needed. The resistors for extending the life of the neon bulbs are not shown, but they can be included if desired, and the circuit operation is not altered significantly by having them there. If a higher spark voltage is wanted, then 2 or more neon bulbs can be used in series, where these circuit diagrams show just one. A point to note is that the lower diode is shown reversed when compared to the previous diagram. This is because the power supply shown is any generic power supply which drives a simple output coil which does not have a center tap. The neon supply of the earlier diagram appears to have 2 separate outputs which will, presumably, be out of phase with each other, as that is common practice for neon sign driver modules. If you wish, the 2 diodes shown here could be replaced by a diode bridge of 4 high-voltage, high-speed diodes. The wire lengths of L1 and L2 are measured very accurately from where the wire diameter changes suddenly, as indicated by the red dashed lines. The L2 wire length is exactly 4 times as long as the L1 wire length, and the L2 wire diameter is half of the L1 wire diameter. How long is the L1 wire? Well, how long would you like it to be? It can be whatever length you want, and the radius of the L1 coil can be whatever you want it to be. The theory experts will say that the L1 coil should resonate at the frequency of the power feeding it. Well, good for them, I say, so please tell me what frequency that is. It is not going to be the frequency of the power supply, as that will be changed by at least one of the neon bulbs. So, what frequency will the neon bulb produce? Not even the manufacturer could tell you that, as there is quite a variation between individual bulbs which are supposedly identical. Actually, it doesn't matter at all, because the L1 coil, and the L2 coil, if you measure them accurately, has a resonant frequency all of its own, and it will vibrate at that frequency no matter what the frequency feeding it happens to be. A coil resonates in very much the same way that a bell rings when it is struck. It doesn't matter how hard you strike the bell or how rapidly you strike it, the bell will ring at its own natural frequency. So the L1 coil will resonate at its own natural frequency no matter what rate the voltage spikes striking it arrive, and as the L2 coil has been carefully constructed to have exactly that same frequency, it will resonate in synchronization with the L1 coil. This means that the length of the wire for the L1 coil is the choice of the builder, but once that length is chosen, it determines the length of the wire for the L2 coil, as that is exactly 4 times as long, unless the builder decides to use an arrangement which has L2 wound in both the clockwise and counterclockwise directions, in which case, each half of the L2 coil will be 4 times the length of the wire in the L1 coil, like this. Mind you, there is one other factor to be considered when deciding what the most convenient wire length for L1 might be, and that is the number of turns in the L1 coil. The larger the ratio between the turns in L1 and the turns in L2, the higher the voltage boost produced by the L1/L2 transformer, and remember that the length of L2 is fixed relative to the length of L1. So, a possible circuit style might be. There are some important points to remember. One is that there must be a sudden change of wire diameter at both ends of each L1 coil and at the ends of each L2 coil. If there isn't, then the connecting wire length will form part of the coil, and if there is some change in diameter but not very much, then it is anybody's guess what the resonant wire length for that coil will be. There can be as many step-down isolation air core L1/L2 transformers as desired, and these do not need to be particularly large or expensive. The builder of the circuit put it together in just a few minutes, using components which were to hand, including the microwave oven capacitor Mark C in the diagrams above. That capacitor is isolated on both sides by the neon bulb spark gaps, and so it will have no modifying effect on the resonant frequency of any of the coils in this circuit. But it is vital to understand that the energy stored in that capacitor can, and will, kill you instantly if you were to touch it, so let me stress once again that this information is not a recommendation that you actually build this circuit. The DC output from the circuit is intended to power a standard inverter, which in turn, would be perfectly capable of powering the high voltage, high frequency input oscillator. One final point is that, as demonstrated in the video, the oscillating magnetic field produced by the L1 coil can power several identical L2 coils, giving several additional power outputs for no increase in input power, because the coupling is magnetic and not inductive as mentioned earlier in this chapter. Please notice that neither the L1 coil nor the L2 coil has a capacitor connected across it, so resonance is due solely to wire length, and no expensive high-voltage capacitors are needed to get every L1/L2 coil pair resonating together. One possible arrangement might be like this, where two of the L2 coils are shown connected together to give increased output power. This arrangement uses low-voltage inexpensive components for the output stages, and there is no obvious limit to the amount of output power which could be provided. As the circuit operates at high frequency throughout, there is no particular need for additional L2 coils to be placed physically inside the L1 coil. However, there can be an advantage to this arrangement in that the wire length of the L1 coil is greater, which in turn makes the wire length of each L2 coil greater, being 4 times longer. This gives greater flexibility when planning the turns ratio of the L1/L2 transformer. The voltage step up or step down of that transformer happens to be in the ratio of the turns, in spite of the fact that this is not inductive coupling and so standard transformer technology does not apply. When you choose the number of turns and coil diameter for L1, that also gives the length of the L2 wire. In order to get the desired output voltage, if perhaps, the step-down ratio is needed to be an amount of 46:1, then you need 46 times the number of L1 turns on the L2 coil. That means that you know both the wire length and number of turns wanted in the L2 coil. But, as each turn will have a length of 3.14159 times the diameter, it follows then that the wanted diameter is the wire length per turn, divided by 3.14159. The wire sits on top of the tube on which it is wound and so has a greater diameter by 1 wire thickness, so the calculated tube diameter needs to be reduced by 1 wire diameter. For example, if the length per turn is 162 mm and the wire diameter 0.8 mm, then the tube diameter would be 162/3.14159 which is 50.766 mm, just over 2 inches. Now for Richard's explanation of the resonant frequency of any length of wire, quarter wave resonance, standing electromagnetic waves. One of the two main types is electrical resonance, is referred to here as quarter wave resonance. This type of resonance depends almost entirely on the length of a wire element for reasons described below. If a segment or length of wire is 1/4 as long as the voltage waves which are traveling through the wire, then a set of reflected waves will be added to the emitted waves, in a synchronized alignment which creates stronger superimposed waves. Accordingly, an understanding of the quarter wave phenomenon will help a reader understand how a straightforward and easily controlled factor, i.e., the length of a wire ribbon which will be used to form a spiral coil, can help create a quarter wave resonant response, which will create the types of electromagnetic pulses and fields referred to as standing waves. The speed at which a voltage impulse is transmitted through a metal wire is extremely fast. It is essentially the same as the speed of light, which travels 300 million meters, 186,000 miles, in a single second. That distance would circle the Earth more than 7 times. If wavelength, in meters, is multiplied by frequency, cycles per second, the result will be the speed of light, 300 million meters/second. Therefore, the wavelength of an alternating current, AC, voltage, at some particular frequency, will be the speed of light, divided by which frequency. Therefore, using simple division, if an alternating voltage operates at a frequency of 1 megahertz, which is 1,000,000 cycles per second, then the wavelength at that frequency will be 300 meters. If the frequency has become 500 kilohertz, the wavelength becomes twice as long, 600 meters, and, if the frequency were to increase to 2 megahertz, the wavelength drops to 150 meters. It should be noted which the term cycles is what scientists call a dimensionless unit, which drops out and becomes silent when other physical terms are multiplied or divided. At AC frequencies of 10 kHz or greater, the common references to alternating current, AC, voltage begin using a different term, which is radio frequency, RF, voltage. Accordingly, RF voltage is a form, or subset, of AC voltage, which operates at frequencies higher than 10 kHz. RF power generators are readily available, and are sold by numerous companies which can be easily located by an internet search, using the term RF power generator. For example, Hotech Technologies Incorporated. HotechTech.com sells 2 RF power generators, called the AG1024 and AG1012 models, which can provide output power at frequencies ranging from 20 kHz to 1 MHz. The 1012 model has a power output of 1000 watts, while the 1024 model has a power output of 2000 watts. The output frequency of any such RF power supply can be adjusted and tuned across the entire range of operating frequencies, merely by turning knobs or manipulating other controls in a power supply of this type. In a wire having a fixed and unchanging length, the easiest way to create a standing wave is to adjust the RF frequency emitted by a power supply with an adjustable frequency, until the tuned frequency creates a wavelength which is 4 times as long as the wire. This principle is well known to physicists, and it is commonly referred to as quarter wave behavior, since the length of the wire segment must be 1/4 as long as the wavelength. Since it is important to this invention, the principles behind it are illustrated in a series of drawings provided in Fig 1 to Fig 4, all of which are well known prior art. Fig 1a indicates an idealized wavelength of an alternating voltage, depicted by a sine wave which is being sent from an AC power supply, shown by a circle at the left end of a horizontal straight wire, into the input end of the wire. The voltage waves travel through the wire towards the right, as indicated by the block arrow in Fig 1a. When the waves reach the end of the wire, they cannot leave the wire, at least, not in a simplified and ideal system, which is being assumed and used here to explain the principle of how a simple straight wire can create a standing wave. Therefore, the voltage wave will effectively bounce or reflect back from the tip of the wire, and the reflected wave will begin traveling back through the wire, going in the opposite direction, as indicated by the left-pointing block arrow in Fig 1b. Because of the laws of conservation of energy, the reflection and return travel of these types of waves, when they bounce off the tip of a wire, is actually quite good, and rather efficient, as discussed below, provided which the wire tip does not emit sparks, arc discharges, or other forms of escaping electrical energy. Accordingly, Fig 1a depicts a set of emitted waves traveling towards the right, while Fig 1b depicts an idealized set of reflected waves traveling toward the left along the same wire. Fig 1c illustrates what happens when both sets of waves, emitted and reflected, are superimposed on each other. Since the two sets of waves are traveling at exactly the same speed, and since they have exactly the same wavelength, they will create a standing wave pattern when they are added together. As can be visualized from Fig 1c, there will be a set of locations, along the length of the wire, which can be referred to as peak nodes, where the AC voltage reaches its maximum. At a location halfway between a pair of adjacent peak nodes, there will be a spot which can be called a null node, a zero node, a through or valley node, or similar terms. At each null node location, the AC voltage will appear to be not fluctuating at all. Those are the sites, along the length of the wire, where each positive hump, created by a sine wave traveling toward the right, will be counterbalanced and offset by a negative hump with exactly the same height, traveling at an identical speed toward the left. As a result, this type of response within a wire creates a standing wave. If the instantaneous voltage is measured at a null node, it would appear that nothing is happening, in terms of fluctuating voltage. Furthermore, the null node will not be moving, along the length of the wire, instead, it will appear to be standing still. This can be demonstrated, in a coil, by using a grounded lead to test for voltages along the length of a coil. If a grounded lead coupled to a voltmeter is used to touch the surfaces of a series of strands in a non-insulated coil, such as a coil made of thin copper tubing, wrapped around a plastic cylindrical shape, as used in the types of large transformers used by hobbyists to create Tesla coils which will emit large and visually impressive electrical arcs, the test lead will detect no apparent voltage at a null node, which will occur at some particular strand in the coil. At a different strand of the coil, the test lead will detect an alternating voltage which has twice the strength and intensity of the voltage being emitted by the power supply. If voltage is measured at a peak node, the voltage will be doing something which can be called, using vernacular or layman's terms, the full tilt boogie. The AC voltage levels will be moving back and forth, between, I, a very high and intense positive voltage, to, an equally intense negative voltage. This is indicated by the bubble shapes shown along the wire in Fig 1c. The bubbles which are shown in Fig 1c can help someone understand how standing waves are created, and how they act in a synchronized manner. However, which drawing fails to show another result which is very important in what actually happens in a standing wave. For purposes of description and analysis at this introductory level, the system can be assumed to be ideal, which implies a perfect mirror image reflection of each wave from the right end of the wire. An ideal system also implies that no reflections occur at the left-hand end of the wire where the power supply is located, and all reflected wave activity simply ceases. In real circuits and wires of this type, second and third order reflections do in fact occur, and they are used to further increase the strength and power output of these types of systems. However, those additional factors and harmonics should be ignored until after the basic principles of this type of system have been grasped and understood. In an ideal system, when the reflected waves, which are traveling toward the left, in the wire segments illustrated in Fig 1, are superimposed on the emitted waves, traveling toward the right, the peak positive voltage which will be instantaneously reached, at the highest point of each bubble shown in Fig 1c, will occur when the positive peak of an emitted wave crosses a mirror image positive peak of a reflected wave, traveling in the opposite direction. Accordingly, when those two positive peak values are added to each other, the instantaneous positive peak voltage which will occur, in the wire, will actually be twice as intense as the positive peak voltage being emitted by the AC power supply. An instant later, at that exact point on that segment of wire, a negative peak voltage will be created, which will be the sum of, I, the negative peak voltage emitted by the power supply, and, 2, the negative peak voltage of a reflected wave also will pass through, traveling toward the left. At which instant, when those two negative peak voltages are added to each other, the instantaneous negative voltage which will occur, in the wire, will be twice as intense as the negative peak voltage being generated by the AC power supply. A more accurate and representative visual depiction of a standing wave in a wire would actually show the heights of the peaks as being twice as tall as the peaks of the emitted voltage waves, and the reflected voltage waves. However, which depiction might confuse people, so it usually is not shown in drawings of standing waves. Accordingly, the instantaneous response in the wire, at a location halfway between two null nodes, is doing something which can fairly and properly be called the full tilt double-double boogie. The double-double phrase, note which it contains not just one but two doubles, was added to that phrase, for two reasons, to emphasize the fact that each and every voltage peak, maximum positive, and maximum negative, will be twice as strong, and twice as intense, as the maximum positive and negative peak voltages emitted by the power supply, and, 2, to point out that the frequency of the superimposed bubbles, shown in Fig 1c, is actually twice as fast as the frequency of the AC cycle which is emitted by the power supply, as discussed below. The twice the intensity result is directly comparable to what an observer will see, if a large mirror is placed behind a light bulb in an otherwise dark room. The mirror effectively keeps the room dark, everywhere behind the mirror, so there is no magical doubling of the light in the room, which would violate the basic law of conservation of energy. Instead, what the mirror does is to shift light away from the backside of the mirror, and keep that light energy on the reflective side of the mirror. Anyone standing in front of the mirror will see two apparent light bulbs. Both of those light bulbs, the original bulb, and the reflected image, will have the same brightness, if the mirror is perfect. Therefore, the mirror will double the intensity of the light energy reaching the observer. That same effect, in a circuit, will happen if the end of a wire acts like a mirror. If a wire does not have any components which will cause it to become an active emission source, which is the behavior of transmission antennas and certain other components, in a way which efficiently releases voltage-created energy into the atmosphere, then the basic rules which require conservation of energy will prevent that energy from simply disappearing and ceasing to exist. As a result, even if the end of a wire is not designed to be a perfect reflector, a large portion of the voltage wave will indeed reflect off the wire tip, and travel back through the same wire, in a second pass. To understand adequately, the type and amount of wave reflection which occurs at a wire tip, consider what happens if a light bulb is shining in a room which has shiny, glossy white paint on all the walls and ceilings, then, consider how it would look if the same light bulb were located in a room with all of the walls and ceilings painted matte black. The total amount of light which would be available, to carry out a task such as reading a newspaper, clearly would be much greater in the white room, because light reflects off white paint, even though white paint does not even begin to approach the type of reflection quality or clarity which a mirror creates. The difference in what happens, when light intensity in a room painted matte black is compared to a room painted a glossy white, does not arise from the presence or absence of reflection quality or clarity, instead, it is governed by the laws of conservation of energy. When light shines onto a surface which is painted matte black, the light energy is absorbed by the paint, and it literally warms the paint up. In contrast to that, glossy white paint will not absorb light energy, so it reflects the light back out, for a second pass through the air which fills a room. Because of the laws of conservation of energy, and without depending on any quality of reflectance characteristic of wire tips, electrical energy cannot simply disappear, when it reaches the end of a wire. Instead, there are only two things which can happen to that energy. The electrical energy can be emitted into the surroundings, such as by emitting sparks, arcs, or radio frequency signals which will carry energy, or, 2, if the energy is not emitted by the tip of the wire, then, by simple necessity and because of the basic law of conservation of energy, it must be reflected back into the wire, and it will be forced to travel back through the wire again. If a wire has a long and tapered tip, then the reflected wave might become somewhat diffused, and it might lose some portion of the clarity of the wave. However, since wavelengths in the frequencies of interest here are hundreds of meters long, the type of tip created by a conventional wire cutter will not create any significant diffusion in a reflected wave. And, unlike the white painted walls of a room, there is not a large area which is available, at the tip of a wire, which can create scatter, spread, or diffusion. As a result, the tip of a wire will be a relatively efficient mirror-type reflector, when an AC voltage is pumped into one end of the wire. The second factor mentioned above, when the double-double boogie phrase was mentioned, relates to a doubling of the frequency of a standing wave. When a standing wave is created in a wire by reflection of an emitted AC voltage wave, the frequency of the standing wave is, quite literally, double the frequency of the emitted wave. This can be seen, visually, by noting that in the emitted AC voltage, shown in Fig 1a, a single complete wavelength contains both a positive hump and a negative hump. Accordingly, 3 complete sine waves, divided into 3 segments by the imaginary vertical lines, are shown in Fig 1a. By contrast, each and every bubble shown in Fig 1c depicts a complete and total wavelength, in a standing wave. 6 of those standing wave bubbles fit into exactly the same length of wire which holds only 3 emitted wavelengths from the power supply. The frequency doubling effect of standing waves is important, because AC systems can convey and release energy in a manner which increases, as the frequency of the AC voltage supply increases. To some extent, this is analogous to saying that, if a motor can be run at twice the speed, while still generating the same torque, then the work output of that motor can be twice as great, at the higher speed. That analogy is not entirely accurate, since work output from an electric device which uses AC power depends on area of the curve functions which occur when sine waves are involved. Nevertheless, as a general principle, if the frequency of the voltage peaks increases, then power output will also increase, in many types of electric circuit components. In the 3 panels of Fig 1, the wire length is 3 times as long as the wavelength of the voltage from the power supply. However, to create standing waves, a wire length does not need to be any particular multiple of the wavelength of an AC voltage. As can be seen by considering Fig 1c, the same types of bubbles would be created, if the wire length were exactly twice as long as the wavelength, or, 2, if the wire length were the same length as the wavelength. Accordingly, Fig 2, which includes Fig 2a showing an emitted wave, Fig 2b showing a reflected wave, and Fig 2c showing the superimposed bubbles, shows what happens in a wire segment which has a length which is equal to a single wavelength from an AC voltage at a fixed frequency. A resonant standing wave will be formed, with a frequency which is double the frequency of the input AC voltage. Which same result will apply, in a wire having any length which is an exact, integer, multiple, such as 1x, 2x, 3x, etc., of the wavelength of the AC voltage being pushed, or forced, driven, pumped, etc., into the wire segment. Moving to still shorter wires, the same principle also applies to any wire with a length equal to 1/2 of an AC voltage wavelength. As shown in Fig 3, which includes Fig 3a showing an emitted wave, Fig 3b showing a reflected wave, and Fig 3c showing the superimposed bubbles, if the wire length is 1/2 of the wavelength, a natural and resonant standing wave will still form, with a frequency which is double the frequency of the input AC voltage. Finally, moving to a still shorter wire, the same principle also applies to any wire which has a length equal to 1/4 of an AC voltage wavelength, as shown in Fig 4a, Fig 4b, and Fig 4c. Even though it does not stretch across or cover a complete bubble, the standing wave shown in Fig 4c is nevertheless a stable, natural, and resonant standing wave, with a frequency which is exactly twice the frequency of the input AC voltage. It is possible to create partially stable and semi-resonant responses, using 1/8, 1/16, or shorter lengths of wire, by using additional devices which can remove electrical power from the system, or which can generate effects which are usually called harmonics. However, those are not the types of natural and stable responses which can be created by a simple, basic system consisting of nothing more than, a wire having a fixed length and a reflective tip, and, 2, an AC power source with a frequency which can be tuned until it creates a resonant response in any wire segment having a suitable length. Therefore, Since quarter wave wire lengths are the shortest lengths which can create natural and stable standing waves, the conventional term which is commonly used, to describe what happens when a wire creates a resonant standing wave response, is a quarter wave response. In some devices, telescoping components, or other elements which can alter the effective length of a wire-type element, can be used to alter the ability of the element to respond to a fixed wavelength. Many types of antennas use this approach, if they need to process signals which are being transmitted on fixed and known frequencies. However, those examples are not relevant to spiral coil reactors, which will use an approach which involves tuning and adjusting the frequency of the voltage which is being supplied to a reactor, until a resonant response is observed in coils with fixed and unchanging lengths. It should also be noted that certain types of tuning elements, such as capacitors, which can have either fixed or adjustable capacitance levels, can also be coupled electrically to a wire, in a manner which emulates adding more length to that wire. This approach can be used to alter, or increase the range of, the frequencies to which a wire circuit will respond resonantly. So, if we have resonant standing wave voltages in our L2 coil and some of that signal passes through the wire connecting one end of the coil to the earth, then what will happen? The best way to check it is to test the way which a prototype behaves. However, if I may express an opinion, I would suggest that the signal passing down the earth wire will be absorbed when it reaches the earth, and that will prevent the signal being reflected back to the L2 coil to upset its operation. Another device of Don's is particularly attractive because almost no home construction is needed, all of the components being available commercially, and the output power being adaptable to any level which you want. Don particularly likes the circuit because it demonstrates COP greater than 1 so neatly, and he remarks that the central transmitter Tesla coil on its own is sufficient to power a household. The coil in the center of the board is a power transmitter made from a Tesla coil constructed from 2 Barker and Williamson ready-made coils. 3 more of the inner coil are also used as power receivers. The outer, larger diameter coil is a few turns taken from one of their standard coils and organized so that the coil wire length is 1/4 of the coil wire length of the inner coil, L2. As before, a commercial neon tube driver module is used to power the L1 outer coil with high voltage and high frequency. It should be understood that as power is drawn from the local environment each time the power driving the transmitter coil L1 cycles, that the power available is very much higher at higher frequencies. The power at mains frequency of less than 100 Hz is far, far less than the power available at 35,000 Hz. So if faced with the choice of buying a 25 kHz neon tube driver module or a 35 kHz module, then the 35 kHz module is likely to give a much better output power at every voltage level. The L1 short outer coil is held in a raised position by the section of white plastic pipe in order to position it correctly relative to the smaller diameter L2 secondary coil. The secondary coils are constructed using Barker and Williamson's normal method of using slotted strips to hold the tinned, solid copper wire turns in place. As there are very slight differences in the manufactured coils, each one is tuned to the exact transmitter frequency. And a miniature neon is used to show when the tuning has been set correctly. The key feature of this device is the fact that any number of receiver coils can be placed near the transmitter and each will receive a full electrical pickup from the local environment, without altering the power needed to drive the Tesla coil transmitter. More and more output without increasing the input power, unlimited COP values, all of which are over 1. The extra power is flowing in from the local environment where there is almost unlimited amounts of excess energy, and that inflow is caused by the rapidly vibrating magnetic field generated by the central Tesla coil. While the additional coils appear to just be scattered around the baseboard, this is not the case. The YouTube video http://www.youtube.com/watch?v $10Hz room 4Z4 feature related demonstrates that the pickup of these coils is affected to a major degree by the distance from the radiating magnetic field. This is to do with the wavelength of the signal driving the Tesla coil, so the coils shown above are all positioned at exactly the same distance from the Tesla coil. You still can have as many pickup coils as you want, but they will be mounted in rings around the Tesla coil, and the coils in each ring will be at the same distance from the Tesla coil in the center. Each of the pickup coils act exactly the same as the L2 secondary coil of the Tesla coil transmitter, each picking up the same level of power. Just as with the actual L2 coil, each will need an output circuit arrangement as described for the previous device. Presumably, the coil outputs could be connected in parallel to increase the output amperage, as they are all resonating at the same frequency and in phase with each other. Each will have its own separate output circuit with a step-down isolation transformer and frequency adjustment as before. If any output is to be a rectified DC output, then no frequency adjustment is needed, just rectifier diodes and a smoothing capacitor following the step-down transformer, which will need to be an air core or ferrite core type due to the high frequency. High voltage capacitors are very expensive. The http://www.richieburnett.co.uk/parts.html website shows various ways of making your own high voltage capacitors and the advantages and disadvantages of each type. There are two practical points which need to be mentioned. Firstly, as the Don Smith devices shown above feed radio frequency waveforms to coils which transmit those signals, it may be necessary to enclose the device in an earthed metal container in order not to transmit illegal radio signals. Secondly, as it can be difficult to obtain high voltage high current diodes, they can be constructed from several lower power diodes. To increase the voltage rating, diodes can be wired in a chain. Suitable diodes are available as repair items for microwave ovens. These typically have about 4,000 volt ratings and can carry a good level of current. As there will be minor manufacturing differences in the diodes, it is good practice to connect a high-value resistor, in the 1 to 10 megaohm range, across each diode, as that ensures that there is a roughly equal voltage drop across each of the diodes. If the diode rating of these diodes were 4 amps at 4,000 volts, then the chain of 5 could handle 4 amps at 20,000 volts. The current capacity can be increased by connecting 2 or more chains in parallel. Most constructors omit the resistors and find that they seem to get satisfactory performance. The impedance of a coil depends on its size, shape, method of winding, number of turns and core material. It also depends on the frequency of the AC voltage being applied to it. If the core is made up of iron or steel, usually thin layers of iron which are insulated from each other, then it can only handle low frequencies. You can forget about trying to pass 10,000 cycles per second, Hertz, through the coil, as the core just can't change its magnetic poles fast enough to cope with that frequency. A core of that type is okay for the very low 50 Hz or 60 Hz frequencies used for mains power, which are kept that low so that electric motors can use it. For higher frequencies, ferrite can be used for a core, and that is why some portable radios use ferrite rod aerials, which are a bar of ferrite with a coil wound on it. For higher frequencies, or higher efficiencies, iron dust encapsulated in epoxy resin is used. An alternative is to not use any core material, and that is usually referred to as an air core coil. These are not limited in frequency by the core, but they have a very much lower inductance for any given number of turns. The efficiency of the coil is called its Q, for quality, and the higher the Q factor, the better. The resistance of the wire lowers the Q factor. A coil has inductance, and resistance caused by the wire, and capacitance caused by the turns being near each other. However, having said that, the inductance is normally so much bigger than the other two components that we tend to ignore the other two. Something which may not be immediately obvious is that the impedance to AC current flow through the coil depends on how fast the voltage is changing. If the AC voltage applied to a coil completes one cycle every 10 seconds, then the impedance will be much lower than if the voltage cycles a million times per second. If you had to guess, you would think that the impedance would increase steadily as the AC frequency increased. In other words, a straight line graph type of change. That is not the case. Due to a feature called resonance, there is one particular frequency at which the impedance of the coil increases massively. This is used in the tuning method for AM radio receivers. In the very early days when electronic components were hard to come by, variable coils were sometimes used for tuning. We still have variable coils today, generally for handling large currents rather than radio signals, and we call them rheostats, and some look like this. These have a coil of wire wound around a hollow former, and a slider can be pushed along a bar, connecting the slider to different winds in the coil depending on its position along the supporting bar. The terminal connections are then made to the slider and to one end of the coil. The position of the slider effectively changes the number of turns of wire in the part of the coil which is being used in the circuit. Changing the number of turns in the coil changes the resonant frequency of that coil. AC current finds it very, very hard to get through a coil which has the same resonant frequency as the AC current frequency. Because of this, it can be used as a radio signal tuner. If the coil's resonant frequency is changed to match that of a local radio station by sliding the contact along the coil, then that particular AC signal frequency from the radio transmitter finds it almost impossible to get through the coil, and so it, and only it, diverts through the diode and headphones as it flows from the aerial wire to the earth wire, and the radio station is heard in the headphones. If there are other radio signals coming down the aerial wire, then, because they are not at the resonant frequency of the coil, they flow freely through the coil and don't go through the headphones. This system was soon changed when variable capacitors became available, as they are cheaper to make and they are more compact. So, instead of using a variable coil for tuning the radio signal, a variable capacitor connected across the tuning coil did the same job. While the circuit diagram above is marked tuning capacitor, that is actually quite misleading. Yes, you tune the radio receiver by adjusting the setting of the variable capacitor, but what the capacitor is doing is altering the resonant frequency of the coil/capacitor combination, and it is the resonant frequency of that combination which is doing exactly the same job as the variable coil did on its own. This draws attention to two very important facts concerning coil/capacitor combinations. When a capacitor is placed across a coil in parallel as shown in this radio receiver circuit, then the combination has a very high impedance, resistance to AC current flow, at the resonant frequency. But if the capacitor is placed in series with the coil, then there is nearly zero impedance at the resonant frequency of the combination. This may seem like something which practical people would not bother with. After all, who really cares? However, it is a very practical point indeed. Remember that Don Smith often uses an early version, off-the-shelf neon tube driver module as an easy way to provide a high voltage, high-frequency AC current source, typically 6,000 volts at 30,000 Hz. He then feeds that power into a Tesla coil, which is itself a power amplifier. The arrangement is like this. People who try to replicate Don's designs tend to say, I get great sparks at the spark gap until I connect the L1 coil and then the sparks stop. This circuit can never work because the resistance of the coil is too low. If the resonant frequency of the L1 coil does not match the frequency being produced by the neon tube driver circuit, then the low impedance of the L1 coil at that frequency will definitely pull the voltage of the neon tube driver down to a very low value. But if the L1 coil has the same resonant frequency as the driver circuit, then the L1 coil, or the L1 coil/capacitor combination shown on the right, will have a very high resistance to current flow through it, and it will work well with the driver circuit. So, no sparks, means that the coil tuning is off. It is the same as tuning a radio receiver. Get the tuning wrong and you don't hear the radio station. This is very nicely demonstrated using simple torch bulbs and two coils in the YouTube video showing good output for almost no input power. http://www.youtube.com/watch?v=KQDCWDC bony, and while only one resonant pickup coil is shown, there is the possibility of using many resonant pickup coils with just the one transmitter. With a coil, fancy name inductor and symbol L, AC operation is very different to DC operation. The coil has a DC resistance which can be measured with the ohms range of a multimeter, but that resistance does not apply when AC is being used, as the AC current flow is not determined by the DC resistance of the coil. Because of this, a second term has to be used for the current controlling factor of the coil, and the term chosen is impedance, which is the feature of the coil which impedes AC current flow through the coil. The impedance of a coil depends on its size, shape, method of winding, number of turns and core material. It also depends on the frequency of the AC voltage being applied to it. If the core is made up of iron or steel, usually thin layers of iron which are insulated from each other, then it can only handle low frequencies. You can forget about trying to pass 10,000 cycles per second, Hertz, through the coil, as the core just can't change its magnetic poles fast enough to cope with that frequency. A core of that type is okay for the very low 50 Hz or 60 Hz frequencies used for mains power, which are kept that low so that electric motors can use it. For higher frequencies, ferrite can be used for a core, and that is why some portable radios use ferrite rod aerials, which are a bar of ferrite with a coil wound on it. For higher frequencies, or higher efficiencies, iron dust encapsulated in epoxy resin is used. An alternative is to not use any core material, and that is usually referred to as an air core coil. These are not limited in frequency by the core, but they have a very much lower inductance for any given number of turns. The efficiency of the coil is called its Q, for quality, and the higher the Q factor, the better. The resistance of the wire lowers the Q factor.